Okay, let's go ahead and get started. Good morning, everyone, or good afternoon on the East Coast. Today we've got a great webinar from 9 a.m. to 1 p.m. So it's going to be a long one on the AMD EPYC Advanced User Training on Expanse. Before we get started, I want to bring everyone's attention to the Exceed Code of Conduct. We are all generally well behaved, but if you observe any conduct that you think is inappropriate, please let us know by sending us a message at exceed.org/code of conduct. And we also want to emphasize that Exceed's committed to providing training events that foster inclusion and show respect for everyone. If you see any terminology that you think is inappropriate, please let us know by sending an email to terminology@exceed.org. Here's the agenda, and I will hand it off to Mary Thomas, who I think is going to do introductions.
All right, Jeff, if you'd just leave that up, because I was going to share the agenda, but that's okay.
Fine.
I'll do it. Okay, great. Thank you. So good morning, everybody, and thank you for showing up for this first EPYC Advanced User Training event that we've had. We have a full morning planned for you, and our goal is at the end of it that you have some skills and tools for doing some of the more complicated work that needs to be done as you port your code to the EPYC processor. So without further ado, I want to go ahead and turn over control to Mark. For each of the talks, we do have a Q&A. Let's go ahead and make him a co-host, Mark, and you can start sharing. Mark is an engineer with the AMD, and so he'll give us a pretty good in-depth overview of the EPYC processors. So without much further ado, Mark, welcome. You're maybe on mute because I can't hear you. Still can't hear you, Mark.
How's that?
Yes, I can hear you now, and I
all
can
right,
see your
all
screen.
right.
The presentation looks good. So
okay.
Thank you.
Appreciate the opportunity to share about the EPYC processors, and hopefully in this short little presentation, you'll walk away understanding the architecture and how that affects your programming of it. Legal. There's the agenda. So just at a high level, you know, there's a traditional monolithic CPUs, and then EPYC took a different path almost 10 years ago we started designing. And the key takeaways here are that you no longer really have a monolithic cache, and there's also because there's so many cores now, you're going to find some resources like IO and memory can be closer to some cores than others, and we've made ways to take advantage of that. So that's just something to always keep in mind. It's just different from what you're used to in the past. Here's a sort of a few of the key aspects of Rome. I'm sure you've all probably read about it, but it has these chiplets, which are CCDs, those compute core die down there. Bit of trivia is that these are the same chiplets used in Ryzen and Threadripper. We just sort them for different market segments. Reliability is key when it comes to EPYC processors. And then we have an IO die. One of the main benefits is that the IO die, having so many pins, is in the larger geometry, 14 nanometer, whereas the chiplets, being cores and cache, really get a benefit from being in 7 nanometer. And we're able to mix and match the technology for performance and manufacturing, which we do in Ryzen as well. Every EPYC processor that we've put out to date has been in the same socket It's an SP3 socket that's characterized by 128 PCIe lanes and 8 memory channels that can run up to 3200 DDR. Just something to keep in mind. Another key takeaway is what we call a compute core complex, a CCX, over there here in the lower left. And that's key because it means a CCX are a number of cores that share the same L3 cache. You know, it's easy to see from the picture that the caches are not going to be contiguous between CCDs, and they're not even contiguous inside the CCD on ROM. Each CCD has 2 of these compute core complexes, these CCXs, where 4 cores, 8 threads share the 16 megabytes of L3 cache. And access to that cache is pretty consistent. A few nanoseconds difference between locations there. See if there's anything else here, but you'll also see from this picture, and that picture there in the middle is very close to what an actual delidded part has. And you can see that there are 2 CCDs in each of the 4 quadrants, and that's really the way it works out whenever when you start looking at it from a topology point of view as you go to pin the different workloads to the different cores. So here's more of a block diagram, and you can see that the 4 quadrants of that IO die, the big gray block in the middle there, you have very symmetrical capabilities. You can hook up at least 2 CCDs into each quadrant. Each quadrant has 32 PCIe lanes, and each quadrant has 2 memory channels. Now, by default, all the memory channels are interleaved so that for the CPU socket, there's 1 NUMA node. But you can set it to break it up into either 2 NUMA nodes, where the left half and the right half, you have 4 memory channels that are interleaved, or for the best performance, you can set it up, memory performance, you can set it up to have 4 NUMA nodes. Now that's a BIOS setting, so I'm not sure exactly what you guys have it set up for, but by putting it into 4 NUMA nodes, I think it's called NPS4 nodes, NUMA nodes per socket, you can see that a couple of CCDs are going to be closer to a pair of memory channels and IO channels as well. So as you think about putting the drivers that service various IO devices, it's good to pin those drivers and support code close, on a core that's within that quadrant to get the best latency and performance. How we make the parts is we populate 2 to 8 chiplets, giving you different product SKUs. Well, you guys have a 64 core, which means 8 CCDs. And I show this to you, not because you're going to go buy different parts, but you can model any of these 48 core, or 32 core, or 16 core devices simply by not pinning code to those cores. Here's what your device looks like. You can see all the cores are active within a CCX and CCD. But if you were to only pin your workloads to every other core, the unused cores, assuming you have power management turned on, would quickly power down. and you would end up having what looks like a 32 core device. And this works really well for machine learning, different type of workloads that really reward a high cache to core ratio. You can see here, you go from 4 megabytes of L3 per core on average to 8. And you can see significant improvements by doing that. Also, if you were to have a high memory bandwidth workload where you just know you're being limited by memory bandwidth, obviously dropping down to every other core, not only would you get that high cache rate, but these cores now have twice the memory bandwidth per core. Just something else you might find helpful. So that's the way we make the parts, and how you can model any of those 8 CCD parts over here on the left, simply by not using the cores and letting them go to sleep. And that extra power and cache will be distributed as needed within the system. So here's the product stack, just at a glance there. Now, NUMA, I've talked a lot about that already, but I'll just reinforce it. Again, you can by default, there's a single NUMA node per socket, and depending on the BIOS setting, you can change that to 2 NUMA nodes. That's the blue line down the middle, or 4 NUMA nodes, and you can see where it's divided up each quadrant. And for most HPC workloads, we find that to be very useful. Obviously, if you have a large set of data that all the cores need access to, leaving it with a single NUMA node per socket works best. Or if you have a legacy code and you just want to run it the way you used to run it on older devices, it's probably helpful just to leave it in a single NUMA node per socket. Talk a little bit about power management. This, you wonder why I'd bring it up and talking about the architecture, but it is important. It's a big difference from what you're used to. The power management inside EPYC is just a lot like what you'd find on your phone or a notebook or a modern desktop processor. It distributes power where it's needed on demand. So like I mentioned before, if you don't pin one of your workloads to a certain core, it'll quickly go to sleep. It can even power off if you leave that enabled. I know there's a lot of habits on older processors to where you turn off boosting at times, thinking that it would give you better latency. You can certainly turn off allowing CC6, which puts it into, you actually power off the cores that are not used. You can disable that within the OS, and that will save you some latency, especially on network type of threads. But doing anything more than that, it's just, it's like 10 nanoseconds, or maybe a little more to come out of CC to come out of C1, the OSC C1. It's very different than what you've seen in the past. And if you've disabled CC6 within the OS, there's no way, if you let it go to C1, that'll ever drop down to that C2, or what we call CC6. I have this graph over here. This is the 7742, which is, I think, the processor that you had. And then legal will not let me show you the code I ran there. But it's not a HPC type code, but there is math involved, and square root, and it's not integer type workload, and it starts off at 3.4 up there. And as you add cores in this particular workload, it drops down to 3.2 gigahertz. So you just can't judge what the base frequency and boost is just by looking at speeds and feeds. We have a very simple spec of a simple base frequency and a simple all core boost max. If we were to run that same workload, but for whatever reason we had a thread going on that was banging away on some PCIe Gen 4 IO devices, well, that IO power would have to be accounted for, and this you would quickly drop. You may start dropping down 50, hundreds of megahertz, just because that IO power is shared with the rest of the CPU. It is a SoC, so just something to keep in mind. If you're wondering why am I not seeing the effective frequency I expected, you may look around and see what else is drawing power within the system. But we do encourage to manage the power not from the BIOS as much as from the OS, and let the chip play its smarts, just like you do on your phone and your notebook to a large degree. It's very good at maximizing the performance for each of the different workloads. Just one more comment on if you disable CC6, because you need the latency, right? You're concerned about that for networking or whatever. It will take away a little bit of power from the overall, allowing the cores to boost. So if at all possible, just let the OS and chip have full reign. I have just a few comments on best practices. It is this is dumb, but it is a x86 64-bit processor. So most of the instructions you're used to will work. AVX 512 is not supported. So there are a few other odds and ends that aren't supported, but they're pretty marginal. You will have, if you're used to running on fewer cores, this will be a challenge, not a challenge, but it's something to think about. You just have to think about how many cores you want to run. You will have a lot more cache per core, and as you get by 32 cores, if you're using all 64 cores, you may even have less memory bandwidth than what you used to have on your 28 or 20 core device that had 6 memory channels. So if you're wondering, I've got double the cores here, why am I not getting double the performance? Just something to think about is that you are limited to eight memory channels that are fast and very efficient compared to what you're used to, but it's still 8 memory channels for 64 cores. Something to think about. Probably the takeaway from this slide is when you're doing your makes, go ahead and use all the cores available on the system. It'll make it go a lot faster if you do that. And the other thing is if you do what we call the hybrid programming, where you have one MPI rank for each L3, and then assign the number of threads for the cores you have within that L3. By default, that'll be 4 cores unless you have SMT or what Intel calls hyperthreading turned on, in which case it could be 8 threads. And just a comment on SMT, most HPC users disable that because, one, you're going to start being limited by memory bandwidth per core anyway. And two, if you're doing a lot of 64-bit double precision floating point, you know, you're sharing a resource between two cores when it could be used very effectively by a single core. Here are some resources. These are all you know, open to anybody who can access the internet. A lot of good stuff there. A lot of good stuff there. If there's something there you don't see, my email is on the beginning of these slides, and just ping me and I'll see if there's anything I can send you that would help with whatever problem you're having there, finding documentation. I had these slides, next few slides will in here for the compiler and libraries, but I know we're going to have some extended sessions later on, so I won't go into a lot of details here. AMD does have an optimized compiler and libraries. We just released a 3.0 version of those. I would say to where we have similar. Well, I think the compiler is the C compiler is very competitive with what Intel offers. The Fortran's getting there. The libraries, the ones we have, are fairly competitive, in some cases better. I think the MKL is a lot broader, and certainly it has the AVX-512. But our compiler is based on LLVM, and it's free. Anybody can access it along with the library and profiling tools. Another little note I was going to point out here is Spec CPU 2017. It's a open source standard. Intel has shared it for years. But what I want to point out is they have a floating point set of tests and an integer set of tests. You can see here's what the tests are. And the good thing is, if you go down, I picked up a 7742 from Dell submission. You can go here and click on this link, and it will take you to those results, very detailed, and it will show you the compile flags used with the AOCC compiler to get the best scores. It's a good jump start for these type of workloads to see how we got our best scores. There'll be some base flags that are applied to all the workloads. And what you might be looking for is more the peak flags that are the individual workloads of how they were tuned by AMD for those various workloads. We said there's a floating point set of tests and an integer set of tests. It's a good jump start if you're looking at what flags to try. One final note on things to watch out for. Almost all the customers that I deal with use Intel tools. They're fantastic, and they work on AMD processors. But there are a few pitfalls. One, don't use the -X. You know, it's going to go out there and see if to make sure you are Intel. And if you're not, it's just not going to be happy with you. There are the workarounds for that. The pre-2020 MKL, it was good to set an environmental flag there on the screen that'll made sure you use the AVX2 in instruction capabilities. The newer 2020, I don't know if it's in the initial release, but maybe the first update, it does pretty well. It does pretty well. They've got rid of that debug flag, but they no longer penalize us as much. So it still works fairly well. Of course, GCC and others have architecture flags built in for AMD processors. Just a little warning there. Some of the ISD codes like MATLAB, you have to make sure if you're using the older MKL to put that debug flag in there. Otherwise, you'll get fairly slow results. And I think that's all the slides I have. I can tell I went through them way too quick. So I guess we can have the questions now.
So Mark, this is Mahidar. Maybe I can, there's a few questions in the chat, so I can read them off.
All right.
Let's see. First one, what's the main difference of the EPYC line of processors to the Ryzen 3000 series?
Oh man, I don't know. It's going to be really bad. I think I have one. I think the difference is the IO die, right? I have one on my computer. I have to look at it. You know, they use the same chiplets, and like I said, we when they're a wafer, we do these electrical tests and we look at the characteristics. And you know, the Ryzens, they have higher boost frequencies, and they don't have quite the stringent reliability, meaning how many years they'll last under what temperature. So same chiplets, so the functionality is the same, but different IO dies, meaning they have within that IO die, we have a data fabric. They're able to run their data fabric faster than what we run ours at on EPYC, and they have fewer memory. They have fewer memory channels. Does that answer your question?
I think that was from William, right? Does that look okay? You can unmute if you need to.
Yes, yes.
Okay, great. I think next one was, does the design that we saw today, how does it change or apply with the 7003 series? I guess that's the next one that just got released today.
Yeah, I've heard of that chip. It's pretty good.
Three gets shared among all. Yeah.
Yeah. So the I mean, there's so many little things that change that add up to big changes. But the one that would affect you guys maybe the most is that we now a CCD now has a single CCX where all 8 cores share a 32 megabyte L3 cache, and the data fabric runs a little faster. So you know, in general, in general, there's times that when we do the cost analysis and show the performance, that the ROM, this is 7002, the ROM chip is a better value, and in some cases performs very well enough. But those are the differences. You know, you have a different core, you have a different core in Zen 3. But it's not like the jump from our first generation Naples to Rome, where it was twice the cores. I mean, it was a huge difference.
Big difference, yeah.
An incremental one.
There was a question about how an end user could control pinning and NUMA layout, and I think we're going to talk about that in my talk. Actually.
Okay. So, yeah. Perfect.
We have some binding scripts that kind of make it easy. We think it makes it easy. We need some feedback. But I think then one thing I wanted to note is we do run with NPS 4 on Expanse.
Yeah. Good choice, which makes that pinning even more important.
So there was a question about whether end users can enable disable CC6. That's a systems group thing, right? I mean, systems admin thing, right? Like you would need to.
Yeah, I don't. Yeah, certainly you can do it from the OS. I just don't know what. Yeah, you would think you'd need some sort of root privileges, but
root permissions. Yeah.
Yeah, I don't know.
But is it? Can it be done without a reboot?
Yes. Yes.
Okay.
Yes. Yes.
That's a good thing to remember.
Yeah.
I think Martin,
like I said, unless you're really worried about latency, like network latency, you know, I would leave it. But you do take a little bit of a penalty coming out of power down, where it has to load back up the cache and all that.
So if it needs to do, and we have to actually figure out if it affects anything else. So Martin, that's a question I can take back and figure out if it's even an option on a production kind of setting to do it actively, enabling and disabling. There was a question about how do I find if the OS supports multi-level L3 cache?
You mean using L3 as NUMA? Or
Martin, you can unmute and ask if.
Yeah, I'm basically just concerned, if the OS that we're running, which is OS 7.3, is having the support for this multi-level L3, as you mentioned, for the EPYC chips. Yeah. If we're running essentially good enough kernel to support this.
Yeah, I know it's certain. I mean, if you do the updates that go beyond the default 7.3, it certainly does. It is aware of the L3, but I don't know. I do not know the settings you'll have to set to make sure that it takes advantage of that. I always think of just the pinning whenever you start your workloads, you pin them, and then you have control of saying I want to share these threads within this L3, and if so that the OS doesn't allow it to jump around. And it's okay if it jumps around, but you could lose like 10% performance. If you had a thread running and the OS decides, it's not being active, so the next time it comes up, it moves it over to another quadrant. You can see where that could be not a good thing. So almost all the HPC types that I work with, they just control it through MPI and OpenMP. Whatever you want.
So that's the wrapper scripts that we'll be talking about.
Right. Yeah. That's the way to do it, and then you don't have to worry about it.
I mean, we did see issues with MPI and pthreads codes where if we ended up with two pthread threads on the same core and really slowed things down.
Oh.
So we had to go and bind them actively after the fact.
I know that's what we do when we do our spec runs too.
There was a question about for precompiled x86-64 code, can you just run them on AMD EPYC? I guess it should be okay as long as you don't have any AVX 512 or some other optimization.
And that you didn't have a lot of time, if you're using the Intel compiler, if you specified an architecture flag, right?
Yeah.
Yeah, and a lot of people do that. I mean, they don't specify the architecture flag, but they have precompiled code and they use it all the time because a lot of times they're running on clusters that had everything from Haswell to Broadwell to Skylake to, so they didn't make it specific to an architecture and ran fine on us.
Yep. And does using fewer CPU cores mean getting more a higher CPU boost?
Yes, exactly.
Yeah,
exactly.
Okay.
But if say you were going to run, you had SMT off and you were going to run eight threads, spread them out. I mean, assuming they don't need to communicate, exchange data between threads. If you spread them out, if you put them all on one CCD, well, they're, we monitor temperature, current, power, hundreds of places, hundreds. I mean, there's 30 something billion transistors, so if you localize all that work being done, then doesn't matter that all the other cores are powered off and nothing's happening on those memory channels. You may hit a thermal limit or even a current density limit, and therefore you'll start throttling. So spread them out if that works.
I think there was a related thing when not running on all cores to improve, I guess, memory bandwidth and per core and other things. Does the power consumption decrease, or is it just boosting up till it actually hits the power envelope?
What could you say that just one more time?
So when you're not using all the cores, so
Yep.
you want to improve the memory bandwidth per core or some other aspect, does the power consumption decrease on the extrude or the overall extruder? Like
For-
your boost is not large enough to take up the power of a idle core, right?
Right, you're going to hit that 3.4. I think yours are limited at 3.4 gigahertz.
Okay.
Yeah.
Yeah.
Yeah. But it definitely will distribute the power, but there, again, there are these local limits.
Limits on each. Yeah.
Yeah. And if I have found that when you're running 32 cores, say every other core on a 64 core device, the bottleneck is out here at the memory controller is where the bottleneck is. When you go to all 64 cores or 128, if you have SMT enabled, the bottleneck is here, up up here on that Infinity Fabric interface between the CCDs. Gives you an idea of what's going on there. Also, I don't know if you guys are running at 3200, DDR, or if you have dual rank. I mean, you have two DIMMs per channel, and you're downclocking to 2933 because of that loading.
I think we are at 3200, but I'll have to go back and check that.
But that's another way, running at 2933, the latency, because the data fabric is running at, was that 1467, whatever the half of 2933, the data fabric taps out at that on Roam. And so it's synchronous at 2933 to that memory. So latency is actually better at 2933 versus 3200. So if you wanted to save power and have better latency, you could downclock your memory to 2933, save some power, get a better boost. All the little tricks. That's another difference with Milan, is that the data fabric runs at 1600 now.
Oh, okay.
Yeah.
So it's quite different. Yeah.
Yeah.
I think the last question is, how does a dual CPU system best share the one PCI slot peripheral effectively, like a NIC or a IB card? Or
Yeah, it's a really good question. You are going to have, the good thing is that when you're in a dual system, you can see how half the PCIe lanes will become the interface over to the second chip.
Okay.
And so it's running much faster than what you're used to. And there's 64 lanes of it. So it's pretty fast, but you do have to come over, whenever you're doing a cluster and go out that one device. Some OEMs, and I don't know which system that you guys have, they take that Gen 4 device and they have an Open Compute 3 standard. Who's the OEM that you guys bought your system from?
it's Dell.
Okay, so Dell has this. I don't know if they put it in your system, but it's really clever. They have that Open Compute 3 on the 7525 there. They put that module in there, and it's Gen 4. And so they bifurcate it and do by 8 to each socket. And since it's Gen 4, you get 100 gigabits off of each of those by 8s, and therefore it is local to that socket.
Oh, that's nice. Yeah,
It's
no, we don't
really
have.
clever.
Yeah, we don't have that because our connection in is HDR 100. So
yeah.
But,
So
but I think I saw this
that.
before.
Yeah, you can have that. Where it's a by on the output are two 100 gigabit slot.
Nice.
Coming out it's really clever. But otherwise, you just come across that, and it's a lot faster than what it used to be. What it used to, but still, you're right. It has to come over that link.
Yeah. I think that was it. If I missed any questions, please either open your mic and ask or raise your hand. Oh, okay. There's one more at the end. How much benefit is seen when using SMT, like with say primary integer workload,
I'll
or
say,
like, or something like gem, like a
yeah,
floating point
I,
compute.
I know on DGEM, when we run it, if we get maybe, so we have 64 cores with SMT off, and you get a score, and if we raise it up, if we turn on SMT, we may get 10% more. It uses more power, of course, and all that. But again, you know, if it's, and it's really good for databases and virtual machines because they're not memory limited. And it, you know, but on DGEM type things, you may see 10% uplift for the node. Could be a little higher, but probably not.
Another question about any tips about maximizing performance for GCC compiled OpenMP Fortran codes?
No, I'm afraid I don't have that experience. You know, obviously we'll use the architecture flags. I'll take a note and see if there's something on our website with guidance on that. So GCC and Fortran.
Yeah.
Okay.
So the question was basically, another question is using one, I guess the follow up on that gem. DGEM thread, so use one DGEM thread per core and then additionally have a non-compute progress thread shared on one of the cores. Has someone done something like that, I guess is the question. We haven't tried this, but
I don't understand the question, sorry.
I guess I can explain.
Yeah, go ahead.
So idea of it, basically you have primarily floating point computations and that would be done on all the cores, and additionally have like a communication progress thread that would be primarily integer shared on one of the cores with SMT. How much benefit is seen by that versus having it just be shared, or basically how much benefit you can get in what is relatively optimal case for SMT.
Right. So when you turn on SMT, the caches are all dynamically shared except for the L1 instruction cache. And so by turning on SMT, all the cores are going to immediately only have half the instruction cache. So everybody would take that penalty. And so if you're not using those other cores, you know, it may be a bigger penalty than what you wanted, you know. But otherwise, yeah, I mean, it's a clever idea, and it might work for you.
All right. Hey, Mark, thank you. I'm going to step in. We're now ready to transition to our next speaker at 10:45, who is Marty Candace is going to talk about the AOCC compiler. So let's go ahead and let him screen share and get him set up to get started. Marty, are you with us and can I hear you?
Yeah, can you hear me?
I can hear you, great.
Okay.
I see your screen.
Give me 1 second.
Thank you very much, Mark. That was excellent. Some great questions, folks. And you can keep asking them and we'll try to answer them as we go. And then there we go. Marty, I see your talk. It looks good.
Okay, great. So thanks everybody for joining us today for this AMD Advanced User Training. My topic today was to sort of give you an introduction to the AMD compilers and math libraries that you might want to try and use with your codes on Expanse or any other AMD EPYC system you might be running on now that they're becoming a bit more popular. Just to preface, I mean, this is sort of my first foray into actually using the AMD compilers and math libraries myself. So hopefully it's not going to be too advanced for most of you. You know, it's really just, you know, my attempt in the last week and a half to sort of try to figure out how to start using the compilers and some of the libraries, and sort of look at some of the performance characteristics and things to look out for when you start testing your codes and benchmarking them. You know, if you're thinking about applying for time on Expanse for your project, if you have some custom code and you need to, you know, submit performance benchmarks to exceed, to, you know, request time and whatnot. So that's sort of some caveats. So there's a lot to cover here. There's a lot of different libraries. I've only been able to sort of touch on a few. So we'll get going. So it's more of a high level overview with a few concrete examples of sort of my experience, basically, for the talk today. So skip over the code of conduct. I think Jeff covered that in the beginning. So yeah, this is sort of the outline for today. I sort of want to first touch on, you know, using the compilers, and then give you a quick example of a code that I sort of, you know, recompiled with AOCC and looked at the performance and just trying to understand, you know, what's available. One thing I'll say off the bat is the naming of the compilers is the AMD Optimizing C compiler on the website, but it also includes Fortran. But I think Mark's slides actually had a different name for the compiler stack, so maybe they're changing the branding. So after we go through just the high level overview of the compiler and some of my initial work there, I'll talk about give you an overview of all the libraries that are currently available. So if it fits within your in sort of your code base to sort of compile against those libraries, you sort of have an idea of what's available. But I'll give you some explicit examples that I use to sort of do some simpler benchmarks against, in particular, the AMD math library and sort of the AMD Bliss library. And then we'll just kind of give you a summary, some references, sort of, I think probably a lot of them Mark might have had on his reference slide as well. And then we'll take a Q&A. And of course, if there's any important questions that come up along the way, hopefully someone on my team stops me and lets me know. So, okay. So, sorry, my Zoom bar is kind of in my way. I can't really see the slides. Okay. So yeah, so the AMD AOCC compiler is really a set of compilers for C, C++, Fortran. It looks like on Mark's slide there, we're talking about Java as well now, maybe. And these are tuned for the AMD EPYC architecture, basically. So this is, I think with this whole new EPYC line of processors, I think this compiler, stack was sort of started, in the first generation to sort of target this new architecture that they have been building out for the last few years. And it's all based on if you're familiar with LLVM, I am not. So hopefully there's not any LLVM questions, or unless someone else in the workshop today has maybe some answers for you, they can maybe answer them in the chat. So yeah, it supports C, C++, and Fortran. And the Fortran compiler is based off of the Flang compiler, and it has sort of some features. There's also OpenMP support across all three languages. It's well tested on the latest operating systems, and for us in particular in the user services group here at SDSC, we're building all of our applications that we provide in the standard software module environment with SPAC. And so we've been actually working a lot with the AMD team who are optimizing certain applications for the EPYC architecture and building the AMD sort of optimized versions for the SPAC packages for those applications. So if you have questions on that at some point, it's probably another topic we can talk about in the future. So just a few things, if you're not familiar with the LLVM tool chain, I would definitely at some point dig into it if you're really going to get into using the AMD compiler stack, since it's all based off of LLVM. I know very little about LLVM other than sort of the basics, of sort of the different pieces that go together with the front ends, the sort of intermediate representation that that things get translated into and then optimize on until your final binary. But essentially, the LLVM part, if you're not familiar with it, you can, as I am not, getting started in the last week and a half or so. The compilers that come with AOCC are sort of, you can just use them end to end, right? You can do a lot more advanced things with LLVM, sort of optimizing in this sort of intermediate representation, sort of stopping the compilation and tweaking things. And there's a lot of advanced things I know you can do, but I have not done that myself, so I will not be teaching that. But there's a lot. If you don't know a lot about compilers, I think LLVM is probably a good thing to learn how it works and kind of give you some ideas of what's actually going on in most compilers. So the C++ support is through the Clang project. So AMD's AOCC, I think, is just a custom derivative of the Clang project. So which supports basically x86 and ARM architectures and the various you see the standard versions of Clang of C that Clang now supports. Again, there's probably a ton of things that you can look into and Clang specific compiler options and things that might work with AOCC that you can find in the Clang documentation, I'm guessing, which is quite extensive as well. On the Fortran side, I'm a Fortran programmer by training myself. So a lot of the examples today are more Fortran heavy. I do have a C example for you. And the one thing I wanted to say about Flang, which I was still learning about a little bit last night, and there's actually a lot of different variants of it. So this is the correct language from the version of Flang that AMD has sort of forked and optimized, or maybe even contributing back to this classic Flang. So if you are a Fortran compiler or a Fortran programmer and you get a little bit confused which version of Flang is the AOCC version based off of, this is kind of the language on the classic Flang GitHub page. And so it's just kind of like, I think, an important note. Looks like there's a lot of history here. And as I'll show you, I think there's probably a lot of, as you can see, there's this note also at the end that, they're planning on replacing this classic Flang in the future. So there's actually, in my opinion so far, from my experience, there seems like there's still a bit of work for maybe some of the Flang support, the Fortran support. But I'll touch on that once we get into it. I have these references at the end, but there are sort of these quick guides for the different compiler options you can use with AOCC. A lot of them are very similar to things you see with other compilers with GCC, Gfortran, the Intel compilers. And so if you have your make file or some sort of build process, you can pretty much take a quick look at these, recompile things with AOCC, whether it's Clang or Flang, and get running pretty quick. And that's kind of what my approach was. It's like, can I take a code that I have now and I've used for years with, say, Gfortran only, essentially in this example, and can I just read the basic documentation, change the compiler options where needed, and see what happens essentially. Right? So that's sort of this example that I want to walk through to start. Let me just check my time here. So this is a code that I wrote probably 10 years ago at the beginning of my PhD. Essentially, it's a simple finite differencing simulation code that solves essentially a sort of more complicated version of the Schrodinger equation to sort of do these simulations of quantum mechanical particles in a sort of one-dimensional ring sort of topology, right? And it's all written in Fortran, essentially probably all Fortran 90. And these are the characteristics of why I chose it, essentially, right? It's sort of pretty simple Fortran, You know, I was not really as advanced of a Fortran programmer as I was. I mean, maybe I'm now, but so it's all mostly basic Fortran 90. It's a serial single core code. There's not any complications of using OpenMP or MPI. It's just straightforward serial code. It's pretty simple and straightforward. There's not a lot of heavy duty work that needs to be done to carry out the simulations that it was sort of intended to look at. However, there are a few things that I wanted to see. I mean, I thought would maybe test the compiler stack and see what the performance was, what features are available, and maybe what ones have been optimized, what ones have not been optimized. So a few things to note, right? So this is sort of a quantum mechanical simulation code. So it's sort of all double precision complex arrays is sort of the large memory component of the code. There's a lot of use of sort of element-wise array operations which are available in Fortran. And then there's a few intrinsic Fortran functions, the sort of complex conversion, taking a complex conjugate of an array, using a sum over an array. And then there's also one of the core things, which is sort of why I chose it too, is there's also a laypack routine that's sort of at the heart of the time stepping process for the simulation. And so originally my goal was to get to the point where I was compiling this against maybe the AMD laypack essentially that they have. I did not get there, but I got some basic results just running the code compiled with different compilers. So I recompiled the code, set up the makefile to use the different compilers, both G-Fortran, which I've only used in the past essentially for this simulation code, compared it with the latest iFort we have on Expanse and the latest version of the AOCC Flang, the 2.2 that we have on Expanse. And these are kind of the basic settings that I always have used for G-Fortran and the translation of those in both for the Intel Fortran compiler and the Flang compiler. And, so pretty basic. Probably most people who've compiled, C and Fortran code are familiar with many of these options. And so it's sort of a one-to-one comparison in most parts. There's a few things that are not that you might notice. Is that, well, I'll stop. Help. Is there? No. Okay. So just looking at the results, you can see that, interestingly, G-Fortran 831 was the fastest of the G-Fortran compilers, which is a little strange because G-Fortran 10.2 is the one that actually has the optimizations for Zen 2, so I'm not exactly sure what's going on there. I did see a note, if you look at that quick guide for the compiler options, that for whatever reason, the recommended GCC version was 9.3 in that guide, which was, I think, the last released in December. So I'm not exactly sure what's going on there, but these are kind of the results. You can see, using the Intel compiler on Expanse's AMD EPYC, it significantly slowed down from the G-Fortran compiled version. And it slowed down even further with the Flang, the AOCC Flang compilers. So I did one check and ran a different Intel compiled version on our GPU nodes, which are actually Intel processors on Expanse, and you can see the performance kind of drop back down to, in the range of, closer to what the G-Fortran compiled version on the AMD EPYC was. And so, what do I think is going on here? There's a few things that may be going on. Obviously, I think if you read any of the details, there's a little bit of chicanery going on with the compilers compiling on different architectures and things between different competitors. So I could be running into those issues here. The one thing that I think may be an issue with the AOCC flang, my only sort of hypothesis is right, this is all double precision complex arrays essentially, and maybe that the double precision complex support is not really there yet. That's the only thing I could think of like what's causing such a slowdown. I mean, it can be completely, I'm not familiar with enough of the compiler options, but that's my only hypothesis right now. So one of the things I did notice though, which I think Mark talked about, is, you know, this is a single core code that I was running, and I noticed that I could definitely visibly see the L3 cache contention, right? So when I was running on a node, which we have, you know, shared nodes on Expanse where, you know, multiple users will be running codes on the same 128 core node. So everybody, you know, you could in theory have 128 different users with a single core running their code on the system. You know, the very noticeable difference when the one node is loaded up with, you know, many tasks, many processes running versus one that's pretty quiet, right? So you will see that kind of cache contention sort of performance hit depending on sort of the random draw, depending on how busy the node is you're running on, essentially. Another thing I noticed, I mean, I don't know if it really had any effect, but, you know, if you look at the output from the compiler options and build warnings that I sort of got when compiling this code, there was a few things that I didn't quite understand. For example, at the bottom here, this warning about these arguments weren't used during compilation. I don't know why it's warning. Maybe these are specific to the Flang compiler, and at some point Clang gets involved in warning about this, because those compiler options were in the documentation. So everything still seemed to work. So, I mean, all the science, I mean, I checked the, you know, energy conservation and things like that, mass conservation in the output. So everything scientifically was working, but, you know, you might get some spurious warnings that might not make sense to you if once you get started. And then there's also, what was something else I wanted to say on this point?
Marty, we have
Yes.
a couple questions that Mahi wants to
Sure.
chime in on.
So I think there were a couple of suggestions in the chat actually. That,
Okay.
mtune actually does sets the instruction scheduling, but you might actually need march to use the instructions for that.
Yes, I did check this. I mean, march or mtune is supposed to set the sort of minimum necessary, I think, to run locally on the architecture you're compiling on, right? And you can actually check this, you know, interactively, essentially, and see what architecture it's using when you set mtune on the specific machine. And I checked that, and it was using the Zen 2. So I don't know. I mean, I can definitely go back and try it explicitly with march. But yeah, I did check this, and I don't expect that to change the results.
The other suggestion, or actually maybe a reason given, is basically if the vectorization is the issue, that the double complex arrays are not going through the LabPAC library.
Yeah, so I mean, so the one thing aside here, with LabPAC, I'm not compiling against any of the AMD libraries. This is a reference LabPAC routine that I've used. It's distributed with the code, essentially. Okay. So this is not using any optimized version of the AMD libraries or any other version of the optimized LabPAC libraries we have on Expanse. So that's why it was like a simple. Like I said, this is very simple code that, you know, I take one LabPAC routine and distribute it with the code. So yes, optimize. I mean, that's sort of one of the goals for this exercise. You know, maybe if I get to linking against some more optimized version of a LabPAC, it'll really speed up the code. So, are there any other questions?
There's a few more suggestions in the chat, I think.
Okay, should we address them, or I don't know?
I think for the most part, there was a suggestion that, yeah, you could do march equals native. That's, yeah, that would work. The PGI question, no, I don't think we've tried it, but we do have NVHPC, but it's on the GPU side, so of the stack, so we can probably try it out on the CPUs and see what we get.
Yeah. Okay. So
I think
like
we
I
can
said,
go ahead. Yeah.
yeah. So like I said, I mean, this is a very straightforward, just convert a makefile to use what I've always used in the past to AOCC and see what happens, basically, right? So yes, I will definitely go back and check with the march native, but like I said, I sort of checked that it was mtune was setting Zen2, so but we'll see. So the second set of the talk, I kind of wanted to back off, like, so I didn't quite have a lot of success with just, using sort of, I mean, performance wise with the AOCC, like just off the bat, I didn't have necessarily, there clearly there's maybe something, an issue there with maybe, like I said, my hypothesis of like the complex math parts of the compiler support. So as I sort of wanted to back off and say, okay, what other sort of concrete examples can I go through? So maybe some more smaller micro benchmarks to test some of the other math libraries and things like that. And so that's kind of what the second part of the talk is about. And so, but I do want to start with sort of a high level overview of just what the libraries are and what's available for you. Because I only really tested the math library and Bliss by the end of the talk. So the AMD math library, or libm, is what you'll see in the documentation, is really just the AMD optimized version of the libm library available basically with any Linux distribution. So a lot of the times when you're compiling your code, it'll be linking maybe without, I mean, if you're not familiar with it, is probably linking against the distribution, the OS distribution of the libm library for some of your function calls, right? And so this is the optimized version. And so this is kind of, if you want to get, I think, start with the AMD optimized libraries and see, what performance gains it might give you, this is probably where I would, start with your own code, right? Next level up, if you're doing any sort of linear algebra, this is the AMD Bliss sort of BLAS library that's available. So this provides all sort of the BLAS functionality you would find in OpenBLAS or MKL for your code. And so I'll do an example of using this as well by the end of the talk. The next step is up in the linear algebra stack is libflame, which is the AMD optimized LAPACK. And so I did not get to using this myself. Sort of kind of was my goal before today, but that just didn't happen. And so, but if you do use a lot of LAPACK routines in your code, this is where you're going to want to go. The one thing that this wasn't necessarily clear to me, coming from the Fortran side of the world, is that it is a C-only implementation, and what the sort of compatibility layer that they talk about provides in terms of supporting Fortran codes. I assume it does support Fortran through this compatibility layer that they're talking about. And I mean, one of the biggest things, if you do a little bit of C and a little bit of Fortran, you know that the memory sort of layout in arrays, sort of the ordering between rows and columns is flip-flopped. And so I'm kind of curious, like what the how they handle that in this compatibility layer to support the performance. But this is, if you're using any sort of LAPACK routines, using Bliss combined with libflame is sort of your library that you'll want to use. And of course, they do also now have a MPI scale pack optimized for AMD as well. And so that covers sort of the one more linear algebra library. So there's also a sparse linear algebra for sparse matrices and vectors that's also optimized. Again, I haven't used it myself, but if you do a lot of sparse matrix operations, this is where you're going to want to go and look at it. Outside of linear algebra, they do have a AMD optimized FFTW library, and I have used this myself actually, not in this talk, but we used it for part of our benchmarking on Expanse for, I think it was NAMD we used it for. Like we got the best.
It's also part of our production quantum espresso build and a few other things.
Yeah. So we have used this to sort of support applications deployed on Expanse and part of our sort of benchmarking, getting the system ready for production. And so so we have seen instances where using sort of AMD FFTW, to compile some of these community codes against gives the best performance on the AMD hardware. So this is definitely one that I've seen results for in production. And then the last set of math libraries are available right now. If you do any sort of Monte Carlo simulations, they have random number generator libraries, both sort of general pseudo random number generation and secure sort of cryptographic random number generation. So this is where you'll go for testing your code against these libraries essentially. So I have not played with it. So the next example is the sort of concrete thing that you can take away from today. And there's code on GitHub that you'll be able to use and play with yourself if you have access to Expanse. This is a very simple example. This example I found in a reference that I'll give later at the end of the talk about this very old benchmark that I'd never heard of before myself, but it goes back to the early 80s. So it's kind of interesting. So this was used in a review essentially of the Zen 1 architecture, assessing the AMD libm performance. Clearly, this loop of 2,500 iterations needs to be a bit larger today. But if you Google this benchmark, you'll find it kind of interesting. People, over the last 30 to 40 years have been also tracking like how well it does on like graphing calculators and things like that. It's kind of an interesting thing. But essentially at the heart of it, what it's doing is trying to assess the floating point performance of these sort of transcendental functions. Essentially, if you look at this inner loop here, you could simplify this in your head. It's really supposed to be A equals A plus 1. So all it does is make a sum, but it makes a complicated sum through these transcendental functions, essentially, right? So mathematically, it converts out it's one of these benchmarks I like where it's exactly what the answer should be, but once you dig into the details and actually do some of the experimental testing, it's kind of interesting. And so yeah, I included the runtime performance of this benchmark back in circa 1983, just for reference. So this is what I got today, essentially. I mean, not today, but in the last week. So this was running just a modern version of this code, this simple benchmark that I wrote last week. And this is when it was compiled against the standard libm distributed with CentOS 8 on Expanse and with different compilers. And there's some interesting results here. So essentially, the number of iterations in this loop that I ran over was essentially n equals, this is 1 million, 10 million, 20 million, 50 million, 100 to a billion, essentially, right? So a little bit bigger than 2,500, but to actually show some differences, I had to sort of scale up. So you'll see that all of the compilers are kind of, do well up to 10 million there's something weird that happens with GCC and AOCC Clang at 20 million. The runtime performance explodes for some reason. I don't know what this is. This looks like a bug of some sort somewhere in not my code, but in maybe somewhere in the library, something gets wedged in a weird spot. And that's kind of my hypothesis. You'll see compiling this code with the Intel compiler we have on Expanse, it scales all the way to the highest number of iterations at 1 billion and gets good performance, relatively compared to the other compilers. And so the reason I'm thinking there's something wrong with there's something wrong in the standard libm with somewhere down the chain there is that I assume that Intel is actually probably pulling out they probably have most of their optimized standard libm functions that are in this benchmark sort of aren't using the one from the CentOS distribution. So they're probably just saying, no, we're going to use our version. And that's why it keeps scaling. That's kind of my assumption. So it's, you really have to dig into like what's maybe, what's coming out in terms of the assembly code to see what's actually going on here. Now, this is somewhat of success. If you compile the same code and link it against, for each compiler, you link it against the AMD libm library, which we have on Expanse. And it's sort of a little bit more complicated to get at it because it's in the AOCC 2.2 module that we have on Expanse. So you sort of have to explicitly link to it. So you sort of have to define a path to it. So if you are doing this, it gets a little complicated because of how we have the module environment set up. You really do just have to point to where it's located on Expanse, if you're using a different compiler, at least. And so you see here that, using the AMD math library, saves the day, at least in terms of whatever that blow up was with GCC and AOCC Clang compiling, linking against libm. And although the performance is still a little bit faster with Intel, right? And so I mean, this is also for the suggestion of using, march versus M2 native. It's kind of showing here that the performance is sort of the same, at least with each compiled on the same architecture. The other interesting note, if you haven't noticed, I guess, is at high iterations, this loop actually goes into like what we would call, I think, dynamical systems a fixed point, which is kind of interesting. And you can actually, I mean, this is I think just an intrinsic issue with the floating point math that's going on. This is not going to change with any compiler, essentially. So whatever this is, so it's kind of interesting. I've kind of seen this before myself, and the reason you can show that it's kind of due to the 64-bit limit, essentially in the floating point computations, is if you actually redo this in Fortran and use a 128-bit math, everything works out fine. So these are just some other observations that I made. The other thing is, right, if you go back to the example, you'll notice that I did not use the fast math flag. And basically, if you do use the fast math flag with any of the compilers, you'll see that what's likely going on is they're symbolically pre-computing. They recognize that, oh, we can simplify that expression to a equals a plus 1 almost. So everything comes out much easier, much nicer in terms of the results. So yeah, in the reference that I'll mention that talks about this benchmark, and you can go look at what they did. They actually did this benchmark with the 030 optimization. So they turned off all optimizations to sort of assess the different performance of the library. So I think this is a little bit more fair, just turning off fast math, which I think keeps the IEE 754 compliance in check. So anyway, so just some other observations and assumptions that sort of are going on with this benchmark. So moving on, the next essentially two examples that I wanted to show was sort of a matrix multiplication example, both using some intrinsic, the intrinsic matrix multiplication in Fortran and the dgem performance from essentially BLAS or AMD Bliss library. So this is a benchmark. So I've used this benchmark before for sort of teaching students about parallel programming. I've used this matrix a lot. So I sort of just put together a bit of code that I've used in the past and sort of extended it to this matrix multiplication example. And essentially it's a simple set of codes that use this Hilbert matrix, which is kind of interesting. It's sort of like that Savage benchmark. It's kind of a quirky benchmark or quirky sort of, set of computations that, might highlight numerical issues, right? So this Hilbert matrix has actually been used in a lot of numerical study of linear algebra algorithms, probably since the 80s too. I think I've seen references to, because essentially it's a very ill-conditioned matrix, but it's very simple to define and set up, and that you can define a lot of analytical results. Like I think, like the eigenvalues and eigenvectors and everything, you know tons of things analytically about this matrix. So when you go and test things numerically, you can see where things break down. So that's why it's kind of useful. It's kind of one of these benchmarks I like, where it's like I can actually write down things analytically and check that everything happened correctly. And so for the benchmark I ran here was I wanted to just take the square of the matrix. So multiply the Hilbert matrix by itself, for some dimension n that I chose. And the check that I performed just to make sure everything seemed to be working was that the first element in the computed results is actually just it basically approaches this pi over squared divided by 6. Right? So again, you can kind of use this benchmark to check things pretty quickly, and if you have like just a little analytical handle on anything you want, any sort of linear algebra sort of calculation that you want to numerically benchmark. And so this is, I did everything in this case in Fortran, just because I wanted to both look at the intrinsic matrix multiplication in Fortran and the support there, right? So this is the results comparing the different compilers. You can kind of see numerically the results that I was checking is all basically the same, down to the base precision, but the performance is wildly different. So G4Tran did quite well again. The AOCC Flang did pretty well, but could be improved. So again, it's possible that maybe just the Flang support for some of the Fortran's intrinsics is not quite there yet. I mean, I don't know for sure. And maybe in the Fortran in the Intel compiler case, it looks like they just don't want to do Fortran well for you for some reason. I did not compare how this runs on an Intel core, but I suspect it probably does better. So the next benchmark that I ran was, okay, let's replace that intrinsic Fortran matrix multiplication with just a standard BLAS routine, so just the standard dgem. And so the first result here was just taking the reference netlib laypack or BLAS laypack dgem, compile that and run it. You can see it does quite poor, which is not surprising. It's just the reference, and it's not really optimized for any architecture or with any sort of modern vectorization and things like that. So the next set of checks was using OpenBLAS, Intel MKL, and libless. And you can see here, all of them do quite well when you link across the different BLAS libraries. So there was almost, very little difference, compared to some of the other results we've seen. The one thing that I guess I did want to note is the Open Blast and AMD Bliss numerical precision is quite the same. So there might be some, I don't know if there's some relation there, but I mean, that's one thing that stood out to me here. But the AMD Bliss, you can see, is still a bit more optimized overall for the set of runs that I did. Don't think there was anything else I wanted to comment here. And that's kind of my initial experience with AOCC and, the AMD libm and AMD Bliss. So very simple, start to learning a whole nother set of tools that, are going to be around for a long time and we'll be using on Expanse for, the next, 5 years at least. And so yeah, I encourage you to, if you're a C++ Fortran compiler or programmer, and you have some of your own custom code that might benefit from both the compiler, the AOCC compiler stack, and AMD libraries, definitely give them a check. As you can kind of see, like, I mean, I can't say that it's going to be obvious when it's going to be performant for you for your specific code and use case, right? You really have to make an assessment yourself and do the checks. And so for example, for me, I'm still curious about using the AMD libflame to see what the support is for my complex tridiagonal solver in the first code that I tried to get started with. So I'll be curious to see how that works out. And that's kind of it. And I have a bunch of references here at the end of the slides. There's links. Those are links to the different guides you can look at. I included here both the AOCC 2.2 guides when available, because that's what we have right now in Expanse. We will be, I'm sure, moving to AOCC 3.0 once we update our module environment on Expanse in the next month or two. And because they just released AOCC 3, I think, last month. There's also, I think, there's all the stuff on the developer.amd.com site. You can check out the individual libraries and resources that they have there. There's, I think, as Mark gave, there's tuning guides. There's even, developer guide manuals, which is sort of even more low-level stuff if you really want to dig into, I think, how the compilers and the architectures work together. And I mean, one thing I do like about the AMD's approach here is you'll notice that a lot of this is open sourced on GitHub, and so you can actually dig into what they're doing, what developments are being made, and what changes are sort of coming down the way, which is a little different, I think, from some of the other vendors we've worked with in the past. And the last set of references I wanted to provide, this is the PRACE computing initiative in Europe. So one of the best guides that I came across, like comprehensive, was this one that they put out last year. It's based on the Zen 1 architecture, but it really covers everything. And they have lots of benchmarks in there for different things that they tested, including this Savage benchmark and a DGEM benchmark. They have, FFTW benchmarks, and really did a lot of work in sort of testing the architecture to understand what was going to be different, essentially, and what you sort of need to take account of when you're developing on this new architecture. And they do also have, I think I noticed that even they have released last year an updated sort of, at least more architecture focused look at the AMD Rome architecture. So for the Zen 2 architecture, they have a nice guide on that as well. So it's kind of where I wanted to end and take any questions that people had.
So Marty, there are a few.
Sure.
So I think one was for the AMD folks. Is there a plan to make AOCL compatible with NB HPC? I mean, you do have the source, so you can actually build this. I haven't actually tried this with the PGI compilers.
So yeah, I mean, I don't know obviously what the AMD's plans are, but I mean, one thing I did notice is that the Flang derivative that they're using is an open source version of the PGI or PGI Fortran. So maybe I don't know. I mean,
I think Mark was going to say something. So.
Okay.
I think that might be changing because that's the classic Flang, right? That is derivative of the open source PGI.
Yeah.
So Mark, I saw you unmute. So if you have to add something.
No, I was gonna say I didn't know.
Oh, okay, no worries. I can follow up on that. And
Yeah, I'm also gonna put some links to where you can get support and questions like this answered.
Okay, that'd be great. Yeah. Dimitri had a question about linking libraries beyond loading the AOCC modules and the other modules. I mean, you will have to obviously add in the link path, but I think other than that, the library names haven't changed on the FFTW and any of the other ones. But Bliss, of course, is a different library. It won't be named EPYC or BLAS. So you'll have to change the link line.
Yeah, and one thing I noticed is with the at least with the the spec packages that we've deployed, you have to explicitly link against the AMD libm, right? It's not gonna, you can't just give the simple L-AMD libm kind of flag. You have to sort of point to where it's located, and it's actually in the AOCC compiler. So if you're linking against it with any other compiler, you kind of have to point back over to the other compiler library, or the AOCC compiler library. And also I think Mahi, I would just comment for anyone who's interested, right? So I think we only have a few of the AMD libraries on Expanse right now, but we'll likely be putting the rest into production at some point. So we have the AMD libm, Bliss. Do we have a libflame? Maybe.
Yeah, we do libflame and FFTW.
And FFTW. I think those are the four that we have right now.
And I think
it would be nice to know where we can see some examples of linking the libraries, if there is anything beyond just the name of the library.
So I would definitely, I mean, this PRACE best practice guide for AMD EPYC definitely has a lot of linking examples. The user guides will have for the different packages, we'll have some. I have a few in these slides that you can look at, yeah.
And Dimitri, we can always add examples to our examples directory if you have any specific things.
Yeah, I mean, for example, maybe I'll add some of these to our examples for on Expanse, just for people.
Yeah, it's just a minor suggestion, just to make it a little more convenient for the users.
Yeah,
okay.
Yeah, definitely. I think Martin, you had a thing saying your experience was that MKL was a little faster than BLAS and Bliss also. I want to say it's true in a lot of cases, but we've seen a few specific instances where MKL has been really poor. And I don't know what the reason was, but we've had a couple of users who've had to completely rework everything to use the AMD libraries and get good performance. Actually, one Quantum Espresso is a good example. I think I had much better performance using the AMD FFTW and the Open BLAS versus going the MKL route for some reason. That was,
hey, Mahi, I'm going to step in so we stay on time and point out that we have a good amount of time at the end for more questions, and I think talking about compiling might be one of them. So let's move on to Mahidar, who's going to speak next. Thank you, Marty. That was really informative. I think putting some of those links from Marty and Mark on the GitHub repository we'll be posting things on would be helpful. So Mahi is going to talk about, Mahidar Tataneni will be talking about Slurm and runtime configurations. I see your window. I know your audio works.
So are we good? Oh.
It looks good, like a presentation. Okay, sure. Thank you.
So I'll get started. So what I'm going to go over is some of the Slurm runtime configurations and kind of tuning in terms of layout and binding that we've looked at. So a lot of the tools that I'm going to be talking about, like the binding and the affinity tools, were developed by Manu Shantaram, and he's on the chat. I think so if there are questions, he'll probably be able to answer better than me, but I can help also. So, so some of this might be a little bit of a repeat. I had it in for completeness sake in case someone picks up this presentation separately. So what I'm going to do is look at the AMD EPYC process architecture, just the hardware details and NUMA options, and so where things it could be an issue in terms of laying out tasks and everything. And then talk about the Expanse task layout and affinity scripts that we developed, and some of the things we learned while benchmarking and helping early users. And all of these are in flux and being modified quite a bit. So, and we appreciate feedback for all of this. So from Mark's talk this morning, you know that basically there were 8 core complex dies on each of the processors. So I have the picture down there. And there are 8 memory channels per socket. So it is DDR4 at 3.2 gigahertz for us. And as Mark noted, you can actually extract the memory and IO, abstract the memory and IO into separate quadrants. And the way we've set it up, and I'll talk about that in a bit later. And then at the core complex die level, there are 2 core complexes, CCXs per CCD. So the 4 Zen 2 cores in each CCX share the L3 cache. So that's core complex there. And there's a total of 16 of these on the node. So you end up with on the processor, you end up with basically 256 megabytes of L3 cache in total. Each core has a private 512K L2. So the way, and there are different ways of booting this up, and the way we've set it up is NPS 4, where it's 4 NUMA domains per socket. So the 4 quadrants are in different NUMA domains, and this is a BIOS option. So if you need to change this, it needs a complete reboot essentially. So I have that circle there as one of the NUMA domains. So basically the memory is interleaved across 2 memory channels, and the PCI devices will be local to one of these NUMA domains. So if, for example, one of those could be the InfiniBand card. And I think on Expanse, I have to go back and check, but it's not on the first NUMA domain. So it's kind of in the middle somewhere. There is, so this is the typical HPC configuration to have 4 NPS 4 with 4 NUMA domains. And what this does mean is that your applications, when you're running their applications, you have to be NUMA aware, and the ranks and memories should be pinned to the cores and NUMA nodes as much as possible. In some cases, it can lead to quite a big performance hit, like pthread codes, for example. So in terms of that kind of the quick overview on the architecture, so let's look at the Expanse task layout and affinity script. So the before I get into that, you can obviously do this with MPI options. All the MPI implementations have affinity options. You can, for example, with OpenMPI, you can use the map by option and say map by L3 cache. And so, for example, this command, I'm running 32 tasks and I'm mapping them by L3 caches. And basically, this was an HPL run, and a node has 32 32 CCXs. So you can basically put an MPI task on each one of them, and then have 4 threads on the same, sharing the same L3 cache essentially. So that's the setup there. Similarly with Intel MPI, you can use pin domain options. And again, these are like not, there are lots of these options. I'm just kind of giving you examples here. So you could do basically, for example, a OMP colon compact in your pin domain options so that you basically get the same layout if you use 32 MPI tasks and four threads. The other things is some of the applications will have their own pinning options. So for example, for an AMD run, this is a 2-node run example that I'm showing here, where basically I have 4 MPI tasks per node, and essentially doing an affinity-based option on this AMD side. So you can see it's doing a plus PP on 31, and wondering why it's not 32. We have some set aside for communication there. You can specifically use particular cores and use a PE map, and that works well too. So that's obviously there are different ways of doing this. Just using MPI options and combining them with, say, application pinning options. But we found that a lot of times it might be more useful to basically use use explicit affinity scripts so that we can lay out the tasks exactly how we want, and also bind them using OpenMP flags and MPI options. So under the covers, we'll be calling srun, but what you see as an end user is just IB run and the affinity. So the basic usage is you just use IB run with the executable and whatever executable options, and IB run will figure out from your Slurm requests what you're actually trying to do, and try to do the best job with it. But you can also use affinity options. So there's another script called affinity that lets you set hints on how you want to lay out the task. And then the script takes care of finding out all the core IDs that it needs to use, and use the appropriate binding options under the covers. So you could be doing this yourself by writing a script that finds out all these things, and then uses KMP affinity flags and all sorts of things to kind of get the right thing. So we've kind of put all that in a nice package. So the various affinity options, so we can do scatter, which will basically scatter ranks. There's a compact option also, but there's scatter option, which will scatter ranks across all NUMA domains in a cyclic manner. You could do scatter CCD, which will scatter the MPI ranks across all the AMD CCD domains in a cyclic manner. You could also do a scatter CCX, which lets you put the ranks across CCX domains in a cyclic manner. So in the HPL example that I was showing with the MPI run before, you could use a scatter CCX option to get the same result, basically, in terms of the layout. We've also kind of given a little bit more control on the scatter options with the block size, so that it's scattering the ranks across NUMA domain in cyclic manner, but then there's a block size of consecutive ranks packed into a single NUMA domain. That way you can control exactly where your MPI tasks land, essentially, by doing different options. So the valid block sizes obviously depend on the CPUs per task that you're using in your Slurm. So one thing to keep in mind is we are using the Slurm requests that you have as the truth in terms of what you want to do. So you have to set the right thing up in that case. And then the domain type, right? Like, so depending on what you have, you can, like on a NUMA domain, you can go up to a block size of 16. On a CCD, you can go to a block size of 8. And on a CCX, you can go to a block size of 4, right? So those are all the things you can do. So this slide was basically a guide for the layout diagrams that I'm going to be showing in the upcoming slides. So imagine these 16 boxes as basically one NUMA domain. And so we have several of these NUMA domains. And then within a NUMA domain, so 0 to 3 there is one CCX, and 4 to 7 is the next, and so on. And this is not related to the physical layout. It's just for you to figure out how things are being, the core numbers that you're using, essentially. So the first example is just using 2 nodes and saying, hey, we're going to have 1 CPU per task and only 4 NPI tasks per node. So we are, and we're running this with no options. So we're just doing IB run. And then it's just going to, by default, cycle across all the NUMA nodes. So you'll end up with task 1 on the first NUMA domain, task 2 on the second NUMA domain, and so on. And then some similar thing repeated on node 2. So this is where you'll see task 1, task 2, task 3, 4, and then 5, 6, 7, 8 on the next node. Now we're using the compute partition again and saying CPUs per task equals 1, and then n tasks per node equals 6. But if you go down here, we are saying, hey, we need to do the scattering, but with a block of 3, right? So then you end up with 3 tasks on the first NUMA domain, 3 on the second one, and then you flip to the next node and so on. So going to the next slide. So what I have is CPUs per task is now moved up to 2. So now if you look at it, the first task, which has actually 2 cores assigned to it, takes up the first 2 cores on the NUMA domain. The second task takes up the next 2, and the third task takes the next 2, and so on. So, but now you still have 3 MPI tasks on each NUMA domain. So you can see how you can use the parameters in the SBatch and the affinity options to kind of spread out the tasks the way you want them. So now if you had gone back to task per node is 2, but said that scatter at the CCD level with a block size of 2, now you see that in the first NUMA domain, the first 2 tasks are core 0 and core 1, but then the first 8 tasks are part of one, first 8 cores are part of one CCD, right? So it's now moving the third and fourth task to the second CCD, which will be core 8 and 9, basically, in the starting with the, or core 8 and 9, basically. So, and then it goes to the next NUMA domain and does the same. So, so you can see how you can use a combination of the particular scatter option and the block option to kind of lay out the task the way you want. Now, if you had gone and done the same thing, but with a scatter CCX option, then you'll see each CCX is basically 4 cores, right? So there was 4, those 4, and so on. So the layout is now going first task on the first CCX, second on the second one, and so on. So all of these under the covers are calling srun and also using the OpenMP binding options to do the layout. So how does this look on the node if you actually look at the task? So I did this with a test HPL run, which wasn't really pushing the node. I didn't allocate too much memory, but basically just to illustrate how this gets laid out. So you have nodes equals 1, and task per node is 32, and CPUs per task is 4. So basically we're using all 128 cores in this run. So we are doing an affinity with scatter CCX. So you'll see basically the MPI task is actually at 100%. The other threads are not quite pushing all the cores to the limit. So it's actually easy to see how things got laid out here. And I'm using, this is output from HTOP. So you can actually log in and look. And once I'm done with the slides to one extent, I'll actually run this interactively and show you how it looks. So basically, we are exposing, putting the MPI task on the first core of each CCX. So that's those 100%. So core 1, core 5, core 9, and so on. And HTOP is nice in the way it shows all the utilization for all the cores. So, and then you can see the threads are all there. So just to confirm, I also logged in and looked at the binding and how it looks. And you can see that core 0 and then core 1, 2, and 3, then it's not in sequence, but all these tasks have the same ID, process ID. So you can kind of see all the so I think there was a question if you use this task, if you enable task affinity equals C group and use the same, yeah, you could probably do it that way too, I think. And I don't know how it will conflict with this.
So what I was trying to ask is when you enable the C group, Slurm is going to pick exact CPUs for you, and you have no idea which CPUs was taken by Slurm unless you define in your SPatch options to tell this is the affinity that I want.
Yeah, you could request
for me.
The core
so if you go with the
yeah.
default n task per node and the CPU per task, you will end up with arbitrary CPU per node. And then if you use the affinity in your IB run, then it just use any of those cores and doesn't care about the affinity.
So we, I think Manu can probably jump in, but basically, I think we are setting them explicitly in the script, in the affinity script.
Yeah, so here, at least in this initial version of the script, we are setting what cores get mapped to what ranks based on the number of tasks you ask. So if Slurm by default is doing some assignment, then it will definitely conflict with IB run. And
that's right. That's what I'm saying.
Yeah.
Yeah.
So right now, the way so if you get the entire node, right now, the way it is getting assigned is you get all 128 cores. It doesn't assign per rank kind of thing. So hence there is no conflict. But if that changes, yes, there'll be conflict.
Right. In the previous slides, you were just asking for like 4 tasks and 1 CPU per task. You don't have any idea that which cores have been picked for your job. And then the affinity, whatever you choose, is not going to work for the IB run.
Right now, it'll work because you are asking for the entire node. So you'll have all
for entire node. Yes, that's right.
Yeah, it doesn't work for shared node.
Yes.
Right. Yeah.
Yes.
Yeah, I should stress that all of this is in compute partition, which is exclusive on our system. On the shared, it gets a lot trickier because I think it's also like almost difficult to optimize at that level because we really don't know which cores we'll get from the scheduler itself because there could be other jobs running that have already mixed up everything, right? We have a lot of single core jobs running on the shared partition. So you will have suboptimal setup no matter what we do, basically. So that almost you have to live with what you get. And I think Marty was kind of alluding to the issue with the shared L3, I think, right? Yeah, we're gonna have that no matter what we do. I think I mean, at this point, we really can't schedule at the at the CCX level or the CCD level, for example. That would be the way to get around what you're saying, Misha, right? So
right. That's right.
schedule at a different level. So
Right.
yeah, so right now we are kind of not thinking about a shared partition when we are doing these things. I think there was a question about.
So if you go to the previous slides,
Oh yeah, sure.
I mean,
This one or the previous one?
Yes, for this case, you're asking for 2 nodes, and then you're asking like 6 tasks and 1 core per task. My assumption is with the node and 128 cores per node, this is going to be a shared job, and you have no idea where those 6 cores are going to land.
Oh, this was more of an example.
Okay.
Like you didn't want to show all the tasks. Like so, our compute partition is actually exclusive. So
I mean, in this case, if you add like s-patch -- exclusive, then no matter how many cores and tasks you're using, you're just basically taking all the nodes.
Correct.
And that should work for you.
Yeah. Which is the case here. The partition compute is exclusive by default.
Right. Okay.
Yeah.
Okay.
So.
Okay, I see. Thanks.
So Omri, you had a question. You have a package that likes setting its own affinity. I think if that's the case, you probably shouldn't use the affinity script, because I presume you know better on how to bind at that level.
Yep, that's correct.
So you just leave the affinity part out, basically. And if you look at the script, it's basically quite simple what it's doing under the covers. It's just we are saving you the trouble of finding all the cores and doing the task set and so on. And thanks, Martin, for that. Yeah, you can just do PS with options to get the affinity info. I think that answers. There's another question above. Run. I think that's your question. So, okay. So one other thing I wanted to talk about is the Slurm affinity setup for the MPI pthreads codes. Now, this was interesting. I don't know if other AMD sites have seen this, but if you have a code that's either just pthreads or MPI pthreads, and you launch it, say, even on a shared compute node environment, what we were seeing was pthreads tasks were essentially landing on the same core sometimes. And it was quite random. Like some runs would work, and then some runs would just hang in the sense they would be 20x slower because 2 of the threads ended up on the same core. So this is kind of the genesis of why we wrote this, or Manu wrote this script, basically the Slurm affinity production script, which basically it's a little bit of a so if your code is using pthreads and your code has the logic to do the right affinity, then this shouldn't be an issue. Like you can set up the affinity yourself in your code. Then that's the optimal way to do it. But what we saw is that there are some applications, community applications, and in particular this issue we showed up with the RaxML code, which is quite commonly used on our system, where they just let the pthreads land where the OS lets them go, and it wasn't an issue, so much of an issue on our systems like Comet or anyone Stampede 2, because the core count wasn't that high and the code was fine using the whole node, and we never saw this issue. But on Expanse, we were seeing that the code doesn't scale beyond a particular core count, or at least it's more efficient at smaller core counts, like I think around 40 or so for the particular test case we were running. And what was happening was, yeah, you would end up in a shared node with threads landing on the same core and ending up with a situation where you would get really poor performance. So this script, what it does is waits for a bit after your job launches, and then actually looks at your Slurm information and looks for the binding that needs to be done and basically binds the threads explicitly. So it's a little bit tricky to use in terms of like it's not a single line like we had for IB run, but what I'm showing here is basically this. On the left hand side is the actual run script. So we have n tasks per node is 10 and CPUs per task is 4. And then what we are doing is an SRun. So it's an MPI threads code. And launching that task, a wrapper script with the options. And on the right, you see what's in that wrapper script, the XML HPC hybrid. So what we are doing is setting up the modules. And this is the script I was talking about, the Slurm affinity production. You don't need the dash test right now. We have it in production. So, and the $exe is executable, and then basically it launches that will be your MPI task essentially, and then that Slurm affinity script will go figure out what to do with the threads and how to bind them. So Manu, I assume you're looking at the MPI task ID and then figuring out which cores to use, right?
Correct. So since this is a shared node, this is for shared node jobs, each rank will have its own set of cores assigned to it. So based on that, you bind the threads to the cores.
So yeah, that's kind of so obviously this is waiting a little bit before it binds. So if your test is real quick, then you won't see it work. But if you have a test that say runs for 20 minutes, Manu, you're waiting for how long do you wait before you do the binding?
So initially, I think it is maybe 10 to 20 seconds, and it polls every second after that.
So that's basically the thing to do. So you will see this with like MPI threads code. They've always been tricky on larger SMPs. We had a similar issue when we were running on our VSMP nodes on Gordon, where the threads would end up in the wrong place. And there, obviously, the penalty was much higher because that node was aggregating physically separate nodes into one virtual node. So a thread moving off a socket meant actually thread moving off to a different physical node, which was really bad. So it's not that bad here, but we did see the lockup or like a real slowdown even in this case because of threads on the same core. It's a little different issue. So those. So let me actually show these like in action before I go to the summary slide. I'm going to stop sharing the thing and so I'm going to move to my HPL directory and submit that job, and then I can also so let me share this. So everyone can see my terminal, right? So
yes.
If you look at so this is the full HPL script. So you can see I have the nodes equals 1, n task per node is 32, CPUs per task is 4. I set up my all my compile. The modules that I use to compile the code, and also doing a module load STSC, which actually puts IB run in your path and the affinity. And this particular run was actually using Bliss. So I have some Bliss specific flags that get set up. And so I'm doing IB run, affinity, and then the scatter CCX and HPL. I'm hoping the machine's not that busy and I'm going to get through real quick. So the job's running now. So I'm going to just go to that node and run an HTOP. So you can see at the beginning, when the memory is being loaded, just the MPI tasks were there, and then now you have the binding that I was showing you in the snap. So, and you can see that it's doing okay. And I have a little wrapper script for what Martin was talking about, which kind of shows where all the tasks are bound, so you can actually see all the binding details. So Martin, you said, would it be possible to share the IP run and thread? Oh yeah, I think so. Manu, we can put it on GitHub, right?
Sure, Mansa, whatever GitHub, I don't know. You can post it to any GitHub.
Yeah, Martin, if you have an Expanse account, you can just grab it from there. It's fine too. With attribution to Manu, that's all. Yeah, definitely. And we would actually, more importantly, I think we would like feedback on how it looks and if there's some other options you want to add into it and so on. Because a lot of this is new. We've used it for some of our tests already. So, but our experience is that users always find some other thing that we didn't think of. So you can see all the layout was fine. I'm going to now I think that's yeah. So this one is the RaxML run that I was talking about, and let me double check here. Yeah, it does have the remove. So let me submit the job there. So now this is the RaxML job, and so you can see this is a shared node. So I'm not using all the tasks, and so yeah, so you can actually see that it's picked some random set of cores. So Misha, this goes to your point about the scheduler might just give us some different set of nodes, set of cores. So which is what's happened here. So you can see I didn't get like a nice contiguous, like even though the node's empty. So
right.
Yeah.
So the node is shared between your job and the other jobs.
Yeah, this could be the case where something else is running on the other cores, and you would get. So this particular pthread script does handle that very well. So we can actually find what Slurm has given us, and then use that for the distribution. Manu, you can add something if you want.
So yeah, this particular RaxML code here, it's a shared node job. So if you ask for say 40 cores, it would give you 40 cores, but it's not specific to either a CCD, CCX, or NUMA. It'll just give you whatever it is, whatever they have.
That's correct.
And the problem with this code was, although each MPI rank say gets 4 cores, some threads in those 4 cores would run on the same core. For example, 1 core would be idle and 3 cores would have 100%, 100%, and 50 and 50% of utilization per thread. So basically something was going on either with OS or I don't know what, that was causing a core to get into that idle state, and that was causing severe performance degradation. So what we did is just spread out the threads across the cores it has been assigned instead of having one idle core. That is what the script does. Was I clear or?
So I think, yeah, I think that's that seems fine. Yeah. So I think there are a few comments in the chat. So Mark, you said that Dell supports CCX as a NUMA domain. So I think the question is more on the scheduling side, like how that would complicate things. I don't know if there's been any work on the Slurm end of things to be scheduling at that level.
Right. That's the question, right?
Yeah.
I'll ask internally, see how we do it, but I do know that people do use that for applications that are to where you don't have control. A lot of telecom applications only look at NUMA. That's about it.
I mean, so we are kind of working around it by using these scripts and doing the best we can do with what's there. But yeah, if we can schedule at the NUMA level, then that's a nice thing.
Yeah, I think what you guys have is really good. I was just thinking of the case where you don't get the entire node.
Yeah.
No, what you guys have is amazing. Really nice.
I think what else is there?
Yeah, Mahi, at this point, we're in the Q&A session for your talk. So
okay.
There's a lot of questions in the chat that I think you're best looking at. And if anybody just wants to open up a mic and ask a question, feel free to do so.
Put the summary slide up. There, and I can look at the question. So just to summarize, basically, we saw the NUMA domain setup with 16 cores on each. We are running NPS 4, so that's the way it's on Expanse. You saw the 8 CCDs per processor with 2 core complexes per CCD and 4 cores in each CCX, sharing the F3. So we have script for MPI OpenMP kind of setup and also for MPI pthreads kind of setup. You can follow us along on Expanse. Oh, I think I have the wrong link, but anyway, I can update this. I think that's one of the links that works, but I was going to point to the Expanse user guide. And then these tools are definitely open for update, and I'm sure Manu and I and others can help if there are questions, and we'll be happy to modify if you find something that's a case that doesn't work. So I think we are good for from the presentation standpoint. I'll walk through and look at the chat and see if something that weren't answered. I think we got most of them in line, but Nisha's question. So the command to find the affinity, I think Martin answered that in the chat a little later. But basically, there are PS options that you can use to find the program. I mean, the binding info. Yeah, I think we are caught up on questions. If you have anyone else has any questions, let me know. So Omri, yeah, I think Manu answered, but yeah, basically the affinity script binds to the set of cores, and the Slurm affinity production script basically binds the threads. So they're basically meant for the second one is meant for pthreads code specifically, because we've seen a lot of cases where that there's no environment variable setup that you can do to bind the processes. So you kind of have to do it.
Well, if there's not any more questions, and there's been a lot of great ones in the chat and a lot of good questions asked to everybody, we can take an early break and return back at 11:55 a.m. Pacific time, where Bob Sinkovitz will give one of his amazing talks on profiling and working with the uProf product that AMD has. And I want to share the screen for a moment, Jeff, if I could, because we've got a couple of links. I have a window here. I'm going to put this in the chat, but if you go to, can you all see my screen showing the training link to this program? We've added a link to the GitHub repository, so that will take you to repo where we're going to put the talks from the presenters. And then it sounded to me like a few key helpful links that we'll add in here, especially some of the ones from Marty's talk, and Mark offered to put a few in there. But you'll be able to come back here in a day or two once we round up all the presentations and get them uploaded to the repository. So I'll put this also into the chat, but just in case you lose it, it's on the training event page, which will stay with this event page and information. And that's it. You're free to get up and roam about the country or your office, wherever you are. Any questions? We'll just keep the Zoom session active, and I'll be around to answer questions if anybody has anything they need to ask. Thanks.
Thanks, everyone.
Thank you, Jeff.
Yep, and it's advancing correctly,
It's
right?
advancing. Yep.
Okay, go ahead. I'll go ahead and stop sharing.
Awesome. Thank you. So we restart.
Okay, let's go ahead and get started. Welcome back, everyone. Thanks for hanging in there. Next, we've got Bob Sinkovitz presenting on profiling applications using AMD uProf. And I'll stop sharing and let Bob take over.
Hey, good afternoon for most of you. Late morning for those of you in California. So I'm going to be talking about the AMD uProf tool. Let me just go ahead and get my slide shared. Okay, everybody seeing my slides?
Yeah, it looks good.
All righty. Yeah, so I'm going to be talking about profiling applications using the AMD uProf tool, and I'll have this link in a few places in my talk. No, let me just go ahead. I'm going to cut and paste. Sorry, I'm just going to cut and paste this. Put this into the chat in case anybody wants to follow along there. Hold on 1 second.
And Bob will also be putting these links on the GitHub repository page for the training session. Thanks.
Alrighty, so diving in, before we start profiling, just going to spend a minute on why we should profile your code. So assuming that if you're profiling your code, you're interested in improving the performance. You want to make it run faster. You want to make better use of your allocation. So I would say for profiling, there are really two things that you're trying to do. First is you want to determine what portions of your code are using the most time. So if you're working on a small application, something that you're intimately familiar with, that you may have written, you probably don't need to profile. You might already have a pretty good idea of where your code is spending the time. But a lot of modern HPC and data-intensive applications are big, often thousands, and in some cases, millions of lines of code. So you really can't just dive in, start at the first function or subroutine and work your way through, trying to optimize it. You really want to know where to focus your effort. And in most cases, you'll find that your time is being spent in just a very small number of routines. And then sometimes you want to go a little bit deeper and you want to figure out why those portions of the code are taking so much time. So understanding why a section of code is so time consuming can sometimes give you valuable insights into how it can be improved. I would say that a lot of us would stop at the first step. I often do that once I've determine the function or the block code that's using the most time, that I pretty much know how to proceed, but I'll be showing an example with the AMD uProf tool of how you can get some additional insight by going a little bit deeper. So AMD uProf is a proprietary performance analysis tool that is just for AMD hardware. It allows you to do profiling in multiple ways. The basic one is what we call the time-based profiling. If you're familiar with gProf, it's very similar. You get a report showing which functions and routines are using the most time. uProf goes a little bit further. It will try to assign CPU time to individual lines of code, which is helpful. But as I'll show, when you are profiling your code with optimization turned on, it's hard to assign usage to particular lines of code, since there may have been transformations of the software by the compiler. If you want to get that information, though, you compile with the -G flag to get symbol information. AMD uProf will provide profiling data in two formats: in CSV files, which we're going to be looking at today. So just regular comma-separated value files. These are human readable. You can open these in spreadsheets. And it also generates a SQLite database that can then be imported into the AMD uProf GUI. Now, in addition to the time-based profiling, you can also access the performance counters to look at cache usage and branch prediction and instruction-based sampling. Today, we're just going to look at cache usage, which I think is the most common use case. So the uProf workflow involves 3 steps. So there's the collect, the translate, and the analyze phases. So in the collect phase, this is when we're going to run the application and generate or collect the profile data. Then in the translate stage, we need to process the profile data to aggregate it and correlate it and save it into the database and the CSV file. And then finally, the analysis step. So the collect and translate, this is analogous to what's going on with gProf, where you first run your code. It will generate a gmon.out file, which is not human readable. And then you would do a translate phase where you would use the profile data along with the executable to then generate a human readable profile. So first step, as I mentioned, is going to be collect. We're going to do that using the AMD uProf CLI bin tool with the collect command. And sampling can be done using a variety of predefined profiles. I'm going to show these on the next 2 slides. Or you could also use the more advanced features and specify specific events. I think in general, though, that you're going to want to stick to the predefined profiles. So we show the generic form of the command here. AMD uProf CLI bin. First argument is collect. That means that we're going to be using this in collect mode, followed by --config, the type of sampling that we're going to do. We then specify -o, the output file, and then our executable followed by the arguments. So the specification of the output and input files is just a little confusing. Here, the output that we specify, it's actually a prefix. So depending on whether you're running in Linux or in Windows, you're then going to get an output.caperf file or an output.prd file. That's then going to be fed into the translate stage. And of course, since we are on Expanse, it's going to be Linux. Let me just check the chat here. How can uProf be loaded on Expanse? Great question. I should have mentioned this earlier. We do not yet have uProf available on Expanse to do these examples. We had one node that was set up. Our system staff is going to be in the process of installing uProf. Turns out it's not a simple installation, since it does require kernel modifications. So it's going to be available soon, and I believe that it's going to be available as a module. But if we have anybody from the systems or user support group here, feel free to weigh in and correct me if I got that wrong.
Yeah, I think that's good. And we may also need a feature if, or depending on how we implement the permissions on the, but yeah, we'll document it as soon as it's available.
Great, thanks, Mahidar. So I mentioned that we have predefined profiles for the collect phase. The basic one is the time-based sampling. It's abbreviated as TBP. And we're going to use this configuration to identify where the programs are spending their time. Think of this as being like gprof, except a little bit more. And then we have a bunch of different profiles. We have, and the next one is, assessing the performance, extended. We can investigate branching behavior, data access, and the abbreviations here, PMU is Performance Monitor Unit, and PMC is Performance Monitoring Counter. Talk about that very briefly. We could investigate instruction access, cache analysis, instruction-based sampling, and kind of a lower level performance assessment. You'll notice that for each of these, with the exception of time-based sampling, that we have a number of PMU events where we're actually monitoring the performance counters. These codes, for example, PMC X076 and so on, they're not going to mean anything unless you go to the unless you go to the user guide and see what these counters actually correspond to. But you could see now the convenience though of having these predefined profiles rather than having to go through the user guides, figure out which counters should be used. So a quick aside on what we call paranoid levels. So in newer Linux distributions, there's a parameter called perf event paranoid. And this controls essentially how many performance counters you can access simultaneously. There are a couple of links here, one in Stack Exchange, one in Stack Overflow, if you're interested in diving a little bit deeper. But once you give users access to the performance counters, it does introduce some security holes. So setting different values for perf event paranoid will determine how many of those counters you could access simultaneously. And we're trying to find the right balance between security and usability. And what we're going to be doing is setting the paranoid level to 1, which is going to allow you to do the time-based profiling and the data access-based profiling. But you'll still be able to access specific counters at this level. So if I go back, I had tried doing branch profiling, and the number of counters, in this case it was 8 counters. It was too large for this paranoid level. But you can always go back, use the more advanced features of uProf if you really want to do branching profiling, and just specify a subset of those counters. I have a question here. Is it possible to integrate uProf with PAPI library?
I think
I don't know.
I think, Bob, I might have asked this question at one of the AMD, and I believe the answer is no.
Okay.
As far as I know. But William, I can double check that and get back to you.
All right, so let me go on. Okay, so the second phase of using uProf is going to be translate. And this is where we take the profiling data and we turn it into a format that we can use. So in this case, we're going to use the same command, AMD uProf CLI-bin. So really important to note here that it's just a single, it's a single tool that we're using for both collecting and profiling. But in this case, instead of collect, we're going to specify report. We have to provide the name of the profile data, the name of the file containing the profile data that was generated during the collect phase. So here we're going to specify -i. We're going to use the same prefix that we did before, output.caprof. In this case, because we're working in a Linux environment, What this is going to do, it's going to generate a new directory named output, which contains 2 files. So it gives you both an output.csv and an output.db. So the former, of course, is the plain text, while the latter is a database file that is read by the read by the GUI. And that gets us to the last phase, and this is the analyze phase. So profiling data can be analyzed anywhere. So my preferred way of doing this would be to install the AMD uProf GUI on my local machine, copy the database over, and use that GUI. But unfortunately, AMD does not currently have an implementation for the Mac. Well, as of at least a month ago, that may have been remedied. But as far as I know, there's still no GUI for Mac. But you always have access to that CSV file. So what I've been doing is I've been taking the output, or the CSV file, and I've been pasting that into Excel. And this actually works pretty well. It requires just a little bit of reformatting, column resizing, and familiarizing yourself with the output. Maybe it's a little bit clunkier than using the GUI, but it still gives you access to all of the information. So now we're going to take a look at a simple example. I put together a toy code, and this is in my Git repo. This is the intro example, where I have a main program, and it calls 2 subroutines, sub1 and sub2. It's going to call sub1 twice. It's going to call sub2 once. And then those subroutines in turn are going to call the functions f1 and f2. So subroutine 1 is going to call f1 n times and f2 n times. And then sub2 is going to call f2 n times. So there's going to be 3 stages in doing the profiling. First, we're going to do our build. Only thing that we need to make sure we do is specify the -G flag so that we get the symbol information. In this case, since we're running on Expanse, I'm going to set the march flag to core AVX2. I'm going to turn on, in this case, I'm going to turn on optimization -03. And you'll see following that in brackets, I specify optionally the inline level, setting that equal to 0. So the optimizing compiler, one of the transformations that the Intel Fortran compiler does is what they call function inlining. What will take the body of a function and it will replicate it where it's called. And this can really boost performance. You avoid the function call overhead, and it also it gives you more opportunities for, say, vectorization of loops. I'm going to name this executable intro, and then we're compiling the intro.f file. Then in the next phase is going to be my collect phase. Again, I'm going to use the AMD uProf CLI bin tool. I'm going to do collect. In this case, I'm going to use the TBP, time-based profiling configuration. I'll specify the output base name is intro-tbp. And I'm going to execute intro. In this case, I'm going to set n equal to 1 billion. And then finally, the translate stage. Again, the AMD uProf CLI bin tool. This time, instead of collect, report. And then I need to specify the profile data. In this case, it would be the intro-tbp.caperf. Just to show you what this code looks like, here's a few key snippets from the code. On the left-hand side is the Fortran main program. You'll see that I'm allocating arrays, W, X, Y, and Z, all to be of size n. This is that parameter that I set equal to 1 billion in the previous example. I'm going to initialize the arrays X and Y. Just set them to the values based on a loop index. And I'm going to call sub1 twice, first with X, Y, and Z, next time with Y, X, and Z, and then finally I'm going to make a call to subroutine 2. On the right side, we see the bodies of these subroutines. So subroutine 1, all it does is element by element. It will call the functions f1 and f2. Subroutine 2, element by element, is going to call the function f1. And then for functions f1 and f2, They just do in this case, kind of a nonsense calculation on the two arguments. In the first case, square root of x divided by square root of y plus y over x. And then in the second case, the square root of the product divided by the square root of the ratio, again, plus ratio. I just put this in here so we have a function that would take up a reasonable amount of time and make our code compute bound rather than memory bound. I see a comment. From William, for uProf usage, are there any particular compiler flags that turn on when compiling? No, you don't need to specify any particular flags. I just used the -G so that we got the symbol information. But unlike gprof, you don't need a specific flag in order to use uProf. Like in gprof, it's the -PG flag. Or sorry, with gprof, it's the -PG flag. So yeah, no, we don't need that. Okay, so this is the CSV output that I get, and I'm not expecting you to read this. This is kind of small, and it's it is hard to read CSV files. But I just want to point out the key sections of the report that you're going to get. Up at the top, you'll see the execution environment and profile details, and this is really handy. It keeps track of which executable you're running, what machine you were running on, the processor architecture, and so on. It's really easy to lose track of that information. You'll then see a section called hot functions. This is a listing of the functions that are accounting for most of the time. And then after that, we get into the function details. So when I did the time-based profiling with inlining, you'll see on the left of the hot functions, you'll notice that we have main there on the top. It's the third line. It used a little over 14 seconds. But you also notice that there's no usage assigned to sub1 or sub2 or F1 or F2. And that's because all of that code was inlined. There was a transformation in the code. So essentially, we now have just a single function. On the right-hand side, though, we can see a breakdown of where time was used in main. Now keep in mind that this is that the assignment of time to individual lines of code is always a little sketchy. I would take these results with a grain of salt. I mean, here it doesn't look too bad. We'll see that F1 and F2 accounted for about 5 seconds and about 7 seconds, respectively, which is what we expect. These were just function definitions that were inlined into the main program, and then a smattering of time in other lines. Now, I went back and I did a profiling with inlining disabled. So again, going back to going to the compilation stage, I added that inline level equals 0 to see how the results would change. And without inlining, you'll see on the left-hand side that most of our usage is with F1 and F2 as expected, some usage by sub1 and sub2, and then also a smattering of time for the system calls. I want to point out, though, on the right-hand side, where we do a deeper dive into the function, this is a case where the assignment of time to lines of code wasn't correct. Again, it's really hard to, especially for optimized code, to assign usage to a particular line. If we look at these first few lines here, function F1, it took about 32 seconds. The line that you think would have accounted for most of the usage, we're calculating the square roots and doing the divisions. Here it was assigned 7 seconds, whereas the statement end function F1 was assigned the bulk of the time. So you can see it's not quite right. Again, take these with a grain of salt. Okay, so I'm going to do a brief digression before demonstrating data access profiling. So what we've been doing with uProf and what we would have done with gprof is using it to figure out where the code is spending most of the time, which functions are particularly expensive. But it doesn't give us any insight into why a particular function is expensive. So for codes with low computational intensity, by this I mean that we're doing a relatively small amount of computation for each word of data that we're operating on. Performance depends on how well we manage data movement. In particular, how well we make use of cache, and uProf gives us access to the performance counters and allows us to go a little bit deeper. So I talked already about memory-bound and compute-bound codes. In memory-bound codes, the performance is limited by how fast we can deliver data to the CPU. And here our goal is going to be to apply cache level optimization so that the CPU is not starved for data. The example that we looked at earlier would be a compute-bound code where the performance of the processor is the limiting factor. We were doing a lot of expensive operations, divisions, and square roots on the data. So we can deliver the data fast enough, and we're just limited by how fast the CPU is. But in real applications, we're often going to see a combination of compute-bound and memory-bound kernels. So continuing in the digression, hopefully a lot of you have seen figures like this already on the computer memory hierarchy, or usually shown as a pyramid, where at the very top we have registers, which are limited. I think modern processors have maybe in the order of 100 registers. This registers hold data that is immediately available for use by the CPU, by the functional units on the next clock cycle. Very, very fast, very small, but of course expensive. Down at the bottom of the hierarchy, we have external storage. We have disk or possibly even tape. Just above that, we have DRAM, our main memory. Typically, this is 100 to 200 gigabytes on modern HPC nodes. But even though memory is fast compared to disk, it's very, very slow compared to the CPUs. So what we like to do is try to move data from DRAM up into the cache hierarchy. So if we look at the L1 cache, which is where we really want data to live, it's small. It's on the order of about 10 kilobytes, but we can access it very, very quickly. This is fast memory that's directly on the processor, and then we'll also have an L2 and L3 level of cache. If you're working on a very, very small problem, all of the data may fit into cache, but in general, your problem is going to be way too large to fit in the cache, so you can only take a small fraction of your data and have it live in cache at any one time. So in order to take advantage of cache, we need to exploit what we call temporal and spatial locality. So the idea of temporal locality is that data that was recently accessed is likely to be used again. So once we load data into cache, we would like to use it again before we have to push it out to make room for other data. Spatial locality means that if a piece of data is accessed, it's likely that neighboring data elements in memory will also be needed. So cache is organized into lines. I say here typically 64 bytes. For modern processors, I've never seen anything other than 64 bytes, and an entire line is loaded at once. So our goal in cache level optimization is going to be very simple. Exploit these two principles to minimize data access times, and in particular, try to minimize the number of cache misses. So we need to look at how data is laid out in memory. So we're going to start with a simple example of a one-dimensional array. This is easy. 1D arrays are stored as contiguous blocks of data in memory. So looking at a little snippet of C code, let's say that we're going to declare 100 integers, assume that they're 4 bytes long. They're going to be laid out with the first element. Element 0, we'll say it has an offset of 0. Element 1 is going to be offset by 4 bytes, element 2 by 8 bytes, element 3 by 12 bytes, and so on and so on. So cache optimization for a 1D array is going to be very straightforward, and you're probably going to write optimal code without even trying. So here's an example where I take all of those elements of the array and I just increment them by 100. So here, the way I would just naturally write the loop, int I equals 0, I less than n, I plus plus is going to access those elements in the right order. So what's going on under the hood? What is well, what's going on with regards to cache? So when we first encounter this loop, the processor is going to load elements 0 through 15 into cache. And then we're going to increment x0 through x15. Then we get to element 16. It's not in cache. We're going to have to load that next cache line. Those next 16 elements, x16 through x31. Increment those. But in reality, the processor is going to recognize the pattern of data access and prefetch the next cache line before it's needed. This is a perfect example of a memory-bound code. We're reading in a piece of data. We're doing a minimal amount of computation, in this case, just incrementing and storing. So we're really going to be limited by the performance of the memory subsystem. In this case, there's really nothing else we can do. The code is already optimal. Question that comes up is, do I have control over cache? The short answer is no. Sometimes we get questions like, oh, is there an assembly language instruction that I can use to say I want to load a particular location in memory into cache? And there's not. The modern processors directly implement advanced cache replacement strategies and branch prediction and prefetch. So I'm going to say the best you can do is just follow the standard practices of exploiting temporal and spatial locality. And that gets us to multi-dimensional arrays. Here's where things get a little more complicated, and you can easily write suboptimal code. So from the computer's point of view, there's no such thing as a two-dimensional array. This is just what we call syntactic sugar. It's a convenience of the programmer. Under the hood, multi-dimensional arrays are stored as linear blocks of data. Here's where it gets a little complicated. There are two ways of doing this. There's column major order and row major order. In column major order, and this is what's used in Fortran, R, and MATLAB, the first or the leftmost index varies the fastest. So if I have this array, this 4x4 grid of numbers, 0 through 15, I'm going to go down the first column, 0, 4, 8, 12, 1, 5, 9, 13, and they're going to be laid out in memory. 0, 4, 8, 12, that was the first column. 1, 5, 9, 13, that's the second column. And so on. Row major order is where the last or the rightmost index varies fastest. And this is used in Python, Mathematica, and C, C++, and the other C-like languages. Here, we're going to go across the first row, 0 through 3, 0 through 3, 4 through 7, 4 through 7, and so on. It would be really nice if there was a single convention, but that's never going to happen. It's kind of like driving. Say in the US and most of Europe, you drive on the right side of the road. In UK and the former Commonwealth countries, you drive on the left-hand side of the road. Nobody's going to make the change. We're kind of stuck with this. So you need to be aware of this as you're working with multi-dimensional arrays. So let's say we wanted to add to multi-dimensional arrays. Our loop nesting is going to be different if we're working with Fortran or we're working with C. So in a properly written Fortran code, note that I have the rightmost index, outermost, the leftmost index, innermost. So I have do I, do j, do j, do I, and then zij equals xij plus yij. Properly written C code is going to flip that around. So we have for I, for j, and then zij equals xij plus yij. And that gets us to performance and how we're going to use uProf. So I put together this code, and again, it's in the GitHub repo, where I measured the runtime for the addition of 2 large n-by-n matrices. And I saw some expected behavior, but I also saw some really unusual behavior. So I ran this for some pretty big matrices, n equal to 32, 767, 768, and 769. When I used the proper loop nesting, this code took a little over 2 seconds to run. A little bit of variation, but pretty much within the run-to-run variation. When I did the improper loop nesting, when I had my loops ordered in the wrong way, it took a lot longer. But notice some of the wild disparities that we're seeing. For the first case, it took about 15 times longer. So nearly 30 seconds rather than about 2 seconds. For the third case, 32769, it took about 10 times longer, to 2 seconds versus about 22. But for that middle case, 32768, it took about 60 times longer. So we're trying to figure out what's going on. As you would imagine, this is a memory bound code. Something's going on with the data access patterns. Remember, we're talking about cache, how cache is so much smaller than the main memory that you can't hold the entire problem in cache. So with the improper loop nesting, we're loading cache lines. We might be using as little as one element of that cache line before it's pushed out and we have to reload new data. So it's bad in all the cases, but it's particularly bad in the middle case, 32768. So what we can do is use uProf and do data access profiling. In this case, I'm going to compile using the G4tran compiler. Reason I did this is that the Intel Fortran compiler sometimes recognizes when you have loops ordered improperly and will re-nest them. I wanted to make sure that the bad version of the code performed badly, that we didn't have that optimization being done behind the scenes. So we compile our code. We're going to collect. Only thing that's different here is that instead of TBP for time-based profiling, we're doing data access. I'm going to do this for both the good and the bad versions of the code. So I call it DMAD good for double precision matrix addition good, or the proper loop nesting, and DMAD bad for the improper loop nesting. And when I do this, if I look at the function details section of the report, I get insight into the cache usage. In particular, these are the number of cache misses that we had for the properly nested and improperly nested codes. We'll see when we use the proper loop nesting that we had about 10 to 11,000 data cache misses. For the improper loop nesting, it was much larger. And in particular, look at the 32768 case, where it was, we went from about 11,000 cache misses to nearly 1 million cache misses. I'm just going to escape here for a minute and show you this in the spreadsheet. Oops, sorry, wrong one. Let's share again. So just to show you the block of code that I was looking at, we'll go back here to the properly nested code. So I'll just highlight. We could see here for this function that we had those 10,419 misses, and this was for the good version of the code using 32768. If we go over here to the bad version of the code, oh, sorry, I realized I need to, no, I'm sorry, that was correct. Here we could see in particular that cell that we had nearly a million cache misses. So this is the kind of information that we couldn't have gotten from time-based profiling, and that we couldn't have gotten with a tool like gprof. Let me just switch back to the presentation. So we would expect that we would have a lot more cache misses when we have the improper loop nesting. But why is it so bad for that middle case, 32768? And it has to do with how data in main memory is mapped to cache. So there are whole textbooks written on this. I won't go into the details. But the location that main memory gets mapped to cache is based on a portion of the memory address. And when we're accessing data with a large power of 2 stride, we keep banging on the same cache lines. So not only was having the improper loop nesting bad, but when we use a problem that was a large power of 2, it was even worse. We kept hitting the same cache line. So we were probably loading that cache line, that entire 64 bytes, operating on just one element, throwing that cache line away to make room for other data that couldn't fit into cache. So just about wrapping up here, where to go for help? This is something I ran into when I first put together this presentation. uProf or muProf? I'm going to say AMD tends to use these two names interchangeably, and sometimes on the same web page or document. If you do a Google search for uProf or muProf for micro, I guess mu stands for micro profile, they seem to yield the same hits for the official AMD pages. So if I look muProf on the left, uProf on the right, these actually take you to the same material. But if I go a little bit further down and I look at the at non-AMD websites, for example, Reddit, Geeks3D, Notebook Check, GitHub, and so on, you'll see that they turn up different hits. And in the case of uProf, there are a few cases where we found unrelated hits. So this second one here on the right side, rib/uProf, I believe is unrelated to the AMD muProf. I see a comment in the chat. Yeah, so Omri, I think I'm answering this. You know, what if you search AMD uProf as opposed to muProf? Yeah, so you're gonna get the top hits for the AMD developer sites. You'll get to the same material, but again, if you're looking at community input, you know, Geeks3D and Reddit and Stack Overflow and so on, you're going to get different hits. So I would say, you know, my recommendation, if you're doing a little bit of digging and you want to go beyond the official AMD documentation, I would probably do both. And with that, I'm just about ready to wrap up. Like I said, we don't have uProf installed yet. What you could do though, if you're interested, is you could read the uProf user guide, and I'll paste this into the chat when we're all done. And then once uProf is installed on Expanse, you can go back. You can rerun these exercises. I'm going to say, you know, try using different compilers, different problem sizes for the intro example where we were looking at time-based profiling. You may want to experiment with the content of functions F1 and F2. You'll get some interesting results if you use sine, cosine, and log functions instead of divisions and square roots. You can go dive a little bit deeper into inlining by breaking the file into multiple files. With that, I'm going to take questions, but let me take a look at the chat first. So there's a question here. What about MPI code? So I haven't, clarified, I mean parallel codes that use MPI. You know, I haven't tried uProf with an MPI code. I think what's going to happen, it's going to be similar to gprof, in that you're going to get a profile per process, which could still be useful. But uProf isn't a tracing tool like Tau. So you're not going to get information about, say, about bottlenecks or load imbalances or communication patterns. And happy to take, we've got a few minutes, happy to take any additional questions. Okay, and we got a question here. How does AMD uProf compare to perf tools? You know, to be honest, I'm not personally familiar with the perf tools. I'm going to guess though that AMD goes a bit deeper. I don't know that perf tools give you access to access to the program counters, in which case you wouldn't be able to get information like cache misses and mispredicted branches. But if we have anybody from AMD or other SCSCers here who are more familiar with perf, feel free to weigh in. Good. Oh, great. Thank you. Thanks, Mark, for posting the link about AMD applications. So, Mark, since you're here, do you want to make any comments on that?
Hey Bob, this is Manu.
Yes.
I think you can use perf to get a lot of cache related stats as well.
Okay.
But I have never tried it on the AMD EPYC, so I don't know about that.
Okay.
So yeah, I think you should be able to get certain events, and those events can be cache events or branch events.
Okay.
Yeah.
And imagine we're even with perf though, we're going to run into the same issues with the paranoid level.
Mm-hmm.
In order, if you wanted to if you wanted to track multiple counters at the same time.
Yeah.
Great. Thanks, Manan. So I'm going to go ahead and stop sharing. Do we have any more questions? I know we've been here for a while. Everybody's brains are probably getting full from all the technical material. Right. Well, Mary, I'm going to hand things back to you.
Thank you, Bob. Nice, nice presentation. Very important for optimizing and tuning on the AMD EPYC processors. So thank you to all our presenters for their really in-depth, informative presentations. We'll be sending out a survey at in the next few days to find out whether, get some feedback from you, or in the Exceed survey, but we might ask our own questions. It's the first time we've done this kind of a workshop, and we thought it was really important for the AMD architecture. And so we have a few minutes dedicated to any kind of questions that you guys want to ask. There were still a lot of questions out there about the compiler and library presentation by Marty, and then the Slurm and runtime configurations. So now's the chance to ask them. And in the meantime, the talks and key links will go on to the repo for the workshop. So anybody want to ask a question or share an opinion or a thought? You guys just want your get out of school pass early today. And that's fine, that's fine. So if you don't have any.
I have a question.
Ah, great.
About compiling in libraries.
Sure. Far away.
I'm actually online right now and trying to compile my code, and I'm trying to use HDF5, and I load the HDF5 module, but I mean, some of the apps like H5 dump and stuff like that show up in the path, but the libraries don't actually show up in my path. And so when I compile, it doesn't find the HDF5 library.
So Tom, I think a few things. There is actually, so HDF5 is, I think, one of the libraries that we have a hidden one that was kind of probably what you picked up. Are you loading any compilers before you do the HDF load?
Yeah, I'm trying various things like the Intel compiler and.
So if you have the right combinations of things, then the only other addition you would have to do is add the path to the library. And we usually set the HDF5 home variable to point to where the actual location is. You can just use that.
Type that in the chat, HDF5 home?
Yeah, I think that's what it will be. Yeah. In caps. So that will be the home. And then /lib should give you the library location, and /include should give you the include path.
It's all one word?
Yeah, it's all one word. Once you load the module, that's set by the module.
Okay. Oh,
So
yeah.
you'll have to modify your makefile or your build script to essentially include the library path, and then it should work fine.
Yep, it's there. Thanks a lot.
Okay, yeah. And if there are any other issues, you can just send in a ticket and we can follow up.
Sure, I will.
Any other questions, comments?
Bob, I think there was one that was for profiling code using libraries. Is there a way to get more detailed symbol information? The debug versions of these libraries, I don't think we do. I have to go back and
yeah, I mean, I think if to support that, I think what we'd have to do is actually deploy some of the package with debug flags on. I have seen that on other systems. Yeah, I mean, if you're interested in that, I think we'll probably have to maybe have to work with you, maybe just install those debug versions in your home directory, and
yeah,
if you're going to do some sort of extensive sort of debugging analysis, maybe. And the question above about the AOCL making sort of some of the libraries like the AMD libm a little bit more accessible. This is one of my sort of maybe feedback comments for our AMD SPAC people at some point is, I don't know the current state of the latest sort of AOCC SPAC package, but to make some environment variables available that people can more easily hook into, versus having to explicitly point the path to where the AMD libm is all the time. So yeah, it's a fair comment that I think we'll probably bring back to our AMD SPAC folks at least. So when we deploy some of these packages in the future, it'll be a little bit more easy to sort of link into them.
Thanks, Marty. Anybody else have any questions or comments or any input you want to share about your experiences on Expanse to date? That would be helpful. Well, it's been a long morning with a lot of, oh, there's a question from Omri Moore, who's one of our experts. Can they take that?
Yeah, I think Omri, that's exactly what we are doing. That's that home variable that I mentioned for each package that gets set. I think the issue is the libm is sitting in AOCC, and if you're building it with some other compiler, then that won't be loaded.
Yeah, SPAC will prevent you from loading the two compilers at once. So it's a little, yeah, that's a particular issue.
Yeah. And if you're wondering why we called it home and didn't use the root, it actually broke some packages because that was a reserved word for some of them. So yeah, for every module that you load, you can just capitalize the module name and then append home to it, and that should be the variable that points to the location.
There's a good question by Ron asking about an automated way to take an MPI code on Expanse and have it run with a bunch of affinity options to see which one is optimal.
None that I can think of. Manu, you want to take a stab at that?
Basically, they can use the IB run and iterate over different flags in IB run. That's what I can think of. Yeah.
All right, well then I want to thank everybody for coming and thank all of our presenters, and thank you guys for working on Expanse and becoming part of our community. Feel free to send us more feedback about workshops of this type or our other workshops so we can determine what information people need as they progress on their work on Expanse. And with that, we'll shut down and say goodbye to everybody. And you guys all have a great rest of your week, and we'll see you online. Bye.
Thank you.
Bye, everyone.